An algorithm is a collection of rules or methods that must be followed when performing calculation or other problem-solving tasks. As a result, knowing how to use algorithm is vital. Although algorithms are independent of underlying programming languages, they should be implemented in any of the available computer languages. The implementation of the algorithm in the Java programming language will be covered in this course. This course will also cover the basics of algorithms and algorithmic analysis, which is the calculation of codes, time, and space complexity. Different programming paradigms such as greedy programming, dynamic programming, and divide and conquer will be discussed. We shall not see only theoretical notions but also real-time application of the same through this course. So without any further ado, let's get started right away. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions, and I will respond to your comments. Now let us very quickly look at the agenda for this course. In this course, we are going to learn about algorithms and algorithmic analysis, linear search and binary search, greedy programming, fractional knapsack, Prim's algorithm, dynamic programming, divide and conquer, merge sort, quick sort, backtracking, recursion.
Let's try to understand what is an algorithm. It is a step-by-step approach to solve a particular problem. If there is a problem, what is the things that you are going to take care of? So the solution that you give should be crisp, right? It should be exactly what is required, right? If a problem is about swapping two numbers, you should be able to swap two numbers and with the most efficient approach. And when you define an algorithm or when you're writing an algorithm, it should be understood by a non-technical person. Right? There should be no such language dependency in your algorithm, right? So this is what an algorithm is, a step-by-step approach to solve a particular problem. Your problem can be complex or it can be an easy problem. It is free from programming language. There are multiple possible algorithms to solve a given problem. Let's suppose I told you to swap two numbers, right? Now, one algorithm is wherein you can go ahead and create one temporary variable and then swap them. The another approach is that you're going to use addition and subtraction operators to solve the same. You're going to use these operators and you can solve this problem of swapping two numbers, right? Which one do you think is the efficient approach? Obviously, here you're using an extra variable and here you're not using any extra variable. So this seems to be a better approach. And obviously, it should be understood by a non-technical person. You should not be using language dependency code, like you should not use any language agnostic code, right? So it should be language independent. So let's see what is an algorithm analysis. This is again a step-by-step approach to solve a particular problem. It helps us identify which algorithm is optimal. Okay, this is the analysis part of algorithm, right? Herein, let's suppose I told you to swap. It helps us to understand the trade-off between time and space complexity, right? So there should be always, you should be able to understand the difference between time complexity and space complexity. And depending on that, you should be able to do a trade-off as well. Now, when I mean trade-off, you should be able to depict that are you going to keep your time complexity efficient, or are you going to use your time efficiently, or are you going to save your space? So let's suppose you are given an example, right? Let me give you an example. So you are given an example, you are given an array, and in that array you want to search an element. Now the first approach is that you will go and search one by one, right? You will go here, you will iterate through here and here and here. You try to search an element, right? Let's suppose you are searching for 4. In the worst case, you are traversing big O of n time, right? And in the best case, you are traversing big O of 1 time. This is the best case and this is the worst case, right? So these are the two cases. But this code in itself, whenever you are traversing in a linear fashion, is inefficient, right? And if you're trying to search for an element using different approach, let's suppose you are using a binary search and then you are trying to search an element, obviously your time complexity will reduce. The best case will again remain big O of 1, but it will reduce to big O of log n. Now, there are certain parameters, or depending on these parameters, you can define the best, worst, and average case of a given problem. So, now there are different types of algorithmic analysis, that those are best case, average case, and worst case. Okay, so the best case is obviously when you are searching for an element in an array of, let's suppose, 100 size, right, or 1000 size. The best case is that the first element that you look, if you're talking about what, linear search, okay, best case scenario is that the element that you're trying to search is the first element, right? Done. This is your best case and it requires constant amount of time. Now if you talk about average case, it will be somewhere around the middle, right? About 1000 divided by 2, or you can say big O of n divided by 2. Since we are neglecting, we do not take care of these constant terms, or we can negotiate, or we can neglect these constant terms, because as soon as our input is increased, right, let's suppose right now we are talking about million thousand elements, we are talking about 10 billion elements, at that time dividing it by 2 still is same, okay, not same, but it can be ignored, because as soon as we are increasing our n, let's suppose, to 10 crore or more than 10 billion, okay, 100 billion is the input size, right? At that time, dividing by 2, still it is greater than what we can do if we have something around log n, okay? So obviously, the average case is still big O of n. Now, when you talk about worst case, the element is found at the end, or it is not even found in the array. You're traversing each and every element in the array and still you were not able to find the element. So this is the worst case, okay? Now the worst case is always taken into consideration because this is the maximum resource that you require, okay? When you talk about time complexity or space complexity, right? So time and space, right? So you always talk about worst case scenario, right? And you always deduce your time and space complexities based on worst case. It is computed because the analysis as it dictates the maximum resource requirements. So worst case helps us to find what are the maximum resources that this is going to take, okay? So we keep track of those things and we allocate resources in such manner. So we always talk about worst case. Now let me give you an example of linear and binary search. So in linear search, right, we always talk about it, and in binary search, the space complexity of both these algorithms is constant in worst case, right? And if you talk about the best cases of linear and binary search, it is again constant, right? And it is again same, okay? Now when you talk about, we go off on, now when you talk about the worst case scenario, right? And this is what helps us to differentiate between binary and linear search, the worst case scenario. The worst case scenario for linear search is big O of n, wherein for binary search it is big O of log n. Now let's suppose there are 8 inputs, you're going to traverse 8 times in this linear search. But if you have this log 8 to the base 2 value, it reduces, or you can reduce it to 3 into log 2 to the base 2, which is 3 times. So in this, you are only iterating 3 times. In this, you are iterating 8 times. Now, as you can see, that input is very low or very less. That means there are only 8 elements. As soon as what our input, our n, or the number of elements in the array grows, this size of these iterations become substantial, and that is for the same reason we always talk about worst case scenario. Okay, now let's talk about time complexity. It determines the total number of unit operations to be undertaken to solve a particular problem. right? Let's suppose, let me take an example of number of iterations. Like, so if you are able to search an element in a single unit of operation, then it is termed to be a constant operation. And if you're doing same for number of inputs, that let's suppose there are n elements and you're traversing to find a particular element, you're traversing n times, so it's termed to be a big O of n. So to solve a particular problem, you determine the number of unit operations. Now, unit operation is an operation that is independent and it can be broken down into simpler operations. It is independent of architecture. It is computed on the basis of algorithm itself. You have an algorithm in place, and based on that, you compute the time complexity of each and every step, right? If there is a loop, what will happen? If there's a if condition, what will happen? If there's a while loop, what will happen? It's high priority critical in optimal algorithm selection. Now, depending on this time complexity, you can determine whether you want to go with a particular algorithm or not. Because let's suppose you're trying to search an algorithm, right? You can have two options, right? You can use a binary search or you can use a linear search. Now, depending upon the time complexity, binary search works much more faster as compared to linear search. It works in order n and it works in big O of n. So time complexity plays a major role, and there is always a trade-off between the time and space. And in this session, we will be covering both of these things. Okay. So now let's take an example and let's try to determine the time complexity of that particular example. Now let's suppose you are given a for loop, and in that for loop, you are iterating from 0 to n, right? Where n is I is less than n, and then you're doing the plus plus. Now you're doing some work in it, okay? Now since you're traversing from 0 to n, now this is a scenario wherein this will be operated or this will work. The number of unit operations that are present in this for loop is big O of n. Now similarly, there is another for loop in the same program which is operating from 0 to n, okay? And then the same thing, there's a nested for loop in it, and therein what you are doing, you are traversing from 0 to what? Let's suppose this is traversed, n is 8, right? N is equal to 8, and in this for loop you are traversing 8 times, and in this while loop you are traversing 3 times, right? Let's suppose you are multiplying every time by 2, okay? So now in this for loop, the nested for loop, the time complexity of the same is n log n. Now, why it is n log n? Because if you observe carefully, number of operations that I told you is 8. So outer loop is working 8 times and the inner loop is working log 2 to the base 8, that is 3 times. So now what is the scenario? What will be the total time complexity? It will be big O of n plus big O of n log n. Okay, this will be the time complexity. Now, since now what is happening over here? This is a scenario wherein what is happening? It is happening m into n. That means you are multiplying big O of n, that is the nest for the nested one, okay, into big O of log n. So you are multiplying it. Whenever you have a situation wherein you have a for loop inside a for loop, therein you will multiply the time complexities. Now you have a for loop outside and then you have this nested for loop. For this nested for loop, you have n into log n, right? And for this, you have what? Big O of n. Now this is a scenario wherein what happens? M plus n. And in this, you will always take into the consideration the maximum number of resources that are there, so that one for loop will take. So in this you're taking only n resources, or this is the time complexity of this is n, and in this you're taking n log n. So obviously this is greater, right? So you always say that the time complexity of that particular problem will be n log n, because you're neglecting these smaller terms. As soon as our input is increased, these terms will be neglected and they will not be that much significant while you're allocating resources. Now, what about the space complexity? It determines the total space to be allocated in order to solve a particular problem. Now, whenever you're using any extra space in the algorithm, while you are implementing it, that is termed to be as space complexity. It can be in the form of arrays, that extra array that you have used to solve a problem, or an extra linked list that you have used to solve a problem, or a stack or a queue, right? It involves memory of the computer, right? You're involving memory, right? You're taking something extra, right, to solve a particular problem. Let's talk about merge sort. Therein you take extra memory, and in worst case you can take big of n extra memory. That means the number of elements that are present in the array, you're taking the same array as an auxiliary memory, that extra memory, right? It's low priority critical in optimal algorithm selection. When you talk about space complexity, we try to avoid any extra space. We try to solve it with minimal space, right? So that we don't use any of these auxiliary memories. Okay. Now let me take an example of a merge sort, wherein in that merge sort, every time you create a left array for the left side and the right side, every time you create these subarrays and then you calculate and then you divide them into further and further unless there is no possible division, and then you start merging them. So again, this is a condition, or this is a scenario wherein you are using extra memory of big of n. Now if you talk about simpler examples, let's suppose you are trying to uh, change the positions of even and odd numbers, right? So let's suppose you have these indexes, right, in the array, and you have some values. Let's suppose 10, 20, 15, 20, 15, and 10. Let's suppose these are the values, right? Now you want to use, or you want to find out the frequency of these numbers. So you will be using another array, and in that array what you will be doing, let's suppose you are picking up this 10 and you are storing it in this. Now you'll be checking, okay, if this is already present, pick up the counter and keep track of how many times this 10 occurred. Now this will work only for when you're trying to search 10 throughout the array. I'm taking a naive example, right? So I'm taking this example and I'm trying to search 10 and I'm trying to calculate how many times it has occurred. So you place a 10 in this array, and then what you're doing, you will just iterate through the array and then keep a track of this, how many times this has occurred, and keep incrementing your counter, right? So now you're using an extra space, right? Now even if this example is not understood, let me take another example. Let's suppose you're using a recursion, right? Now you might be thinking, okay, internally you are not using any extra space, but what happens in recursion? Every time a recursion is there, that means function calling itself, an activation record is created and a stack is used internally, wherein your main function will be there and the number of function calls, right? The function calling itself, function calling itself, function calling itself will be we will be pushing it on the stack, and once you have returned, then we will be popping it out, right? So internally you are using an extra memory, and it depends on from program to program. Are you using big O of n, or are you using log n space? But internally recursion uses extra memory. So an auxiliary memory, or you can say that extra memory, is used while you are using recursion. So that is why we try to avoid recursive problems, and we try to solve our problems using iteration. So, which is obviously that we are not using any auxiliary memory, although it is internally, but still recursion uses extra memory, and that thing is taken into consideration. Now, you might be thinking, okay, now should we use, or should we save space, or should we use less time? Should we go for time efficient algorithm or space efficient algorithm? Now, there is always a trade off between space and time. So, in some problems, they might ask you to save or to write an efficient algorithm, keeping the time into consideration, that you don't have to use extra time. But in some, they might say, okay, you can use extra space, but time should be efficient. Or in some cases, they say you use as much time as you want, but space should be less. So that is also there. So there's always a trade-off between both of these things.
Now let's see how we can find the time and space complexity of any given code or algorithm. So basically here I'm going to give you some tips and tricks when it comes to finding the time complexity of any given code, or for that matter even space complexity for any given code. So what happens in any programming language? There are certain constructs or certain programming, concepts which we use. Like for example, conditional loops, conditional statements, then no looping constructs. So nested loops. So how does time complexity is found or in these cases? And also the space complexity, like what is the total space being taken while executing that particular code? No space, when I talk about how many variable at a time resides in memory, that decides the space complexity. Okay, and time complexity is again the total time taken, maybe in terms of n we calculate. If suppose n is a number of input, so if n or 2 is a number of input, so for 2 input, what is the total time taken for each code to run or to execute? So we'll assume there are n inputs, and for n given input, how many times the particular code runs, that decides your time complexity. Okay, so I'm going to talk about few small tips and tricks about finding space and time complexity to you, starting from the first aspect, that is your looping constructs. Okay, so if I talk about loop, the very frequently used loop is your for loop. So let's see if int I is equal to 0, and it goes till I less than n and I plus plus, and then there is some statement here, maybe x is equal to y plus z. Let assume that all these variables were declared before in any programming language for that matter. Okay, so what will, if I tell you that, okay, find out the time complexity, what time this complete code is going to take if n is the input. Okay, what you will do is, okay, if I assume there is no the number of input is only one, so the for loop will run only one time, and this complete statement will run only one time. So time taken is only 1 unit of time, right? And what will be the space taken that time? Only this variable, these two variables will be stored at a time in the memory, right? So no matter what is the input, every time you need only two variables at a time to be stored there in memory. And when the sum is done, that is discarded, and then only there is only one variable then after that, right? So space complexity is constant here, right? Only 1 unit of space is taken, because every time, no matter how much is the input, every time that same two variables occupies the space. So space here complexity will be O of 1, but time complexity will be, for one element, this for loop will run only one time. So time complexity will be also 1 unit of time it is going to take. For two no elements, this for loop will run two times. Similarly, for n elements, this for loop is going to run n times. So the statement will be executed how many times? N times. So we can say that it takes O of n unit of time. Okay, big O of n unit of time it takes to run the code. Okay, now coming to the another thing is your nested loops. Okay, so guys, whenever you find the smaller codes, you can fragment together and find out the overall time complexity for any larger code. So talking about nested loop. So nested loop, how it runs, for is int, suppose I is equal to 0, I less than n, I plus plus, and then inside this there is one more for loop. Okay, maybe int j of 0 to j less than n, j plus plus, and then this there is a statement, maybe same statement I'm writing, int x is equal to y plus z, and then this closes the bracket. Now how many times this code will run? Again, space complexity is going to be O of 1, guys, because you can see the actual operation being done is only this, and every time it requires 2 unit of space. So it's constant throughout the execution. It doesn't depend on the number of inputs. So it is O of 1, the constant time, the constant space. Talking about time complexity. So you see here, for each value of I, j runs from 0 to n. So if value of I is 1, or you can say value of I is 0, then this runs from 0 to n, that is n times. If value of I is 1, then also this runs from 0 to n times. If value of I is 2, then also this runs from 0 to n for n times. Similarly, so on. Okay. It means if this goes from 0 to n, this will also go from, for each value of I, it is going to go from 0 to n. 1 to n, because it's less than, not less than, equal to. Or you can say 0 to n minus 1. Right? It means what? For I value as 0, this code runs n times. Then I value of 1, this code runs n times. I value of n, this code will run n into n times. Yes or no? Like, are you getting my point? So this is mathematical concept here. So n into n, that is the time complexity for this will be O of n square, right? Now, coming to the third type of a concept, if else loop, conditional statement. Okay. So if says if, and there is some statement over here. Okay. Then it says else, and then some statement over here. Suppose the time complexity of this is O of n, and time complexity of this is O of n square. Which will be the final time complexity out of this complete if else loop? Final time complexity will be whichever part of either if or else, whichever part has less time complexity, which is taking less time to execute. If this is taking n times to execute, this is taking n square times to execute, definitely n is smaller, n is lesser value than n square. So the overall time complexity for out of this if else loop will be O of n. Is it clear? Right. Okay. So this is your these are the three constructs. Now let's see if there are sequential statements. Like definitely in any given program, there's not only just for loop or just a nested for loop or if else loop. There are other statements also along with these loops. So in that case, how the time complexity or space complexity is taken care. Again, guys, here I'm not told about space complexity in this if else loop. So space complexity again depends on what statement is being over here. Like at a given point of time, how much is the space being occupied in memory to execute that statement. Does that space allotment depends on the number of input? Then how it depends on number of input will be your space complexity. Otherwise, it always remains constant. Fine. Let's see the fourth aspects where there are other statements also along with these looping constructs and conditional statements in a given program or a code. So now the fourth condition which I'm going to see here is that suppose there is a statement, x is equal to y plus z. Okay. Then there is a for loop over here. Then there is maybe do while loop, so it does something, and then while loop is there. Okay. Then there is again maybe some statement some statement here, maybe a is equal to a plus plus. Fine. Now let's see from, so what you'll do is you'll start from the beginning of the code. So first code here takes how much time? Is it dependent on the input? No, every time it's going to be y plus z only, no matter input is 1 2 3 or whatever. So it is constant time. Suppose this for loop, whatever is the for loop over here, this takes time complexity of O of n. Okay. Then there is this do while loop, which also takes the time complexity of O of n. Okay. Then there is this a is equal to a plus plus statement, which takes constant time. Okay. Then in this case, what will be the final time complexity? So the final time complexity is going to be the summation of all, that is 1 plus n plus n plus 1. Okay. And this will be your, so constants are always removed because it doesn't play much role, because constant is going to be always taking constant time. So that doesn't affect our performance, right, of the code. So we'll remove those n and n. So n plus n will be 2 of n, right? Again, this is a constant which will be eliminated, and this will be just n, right? So the total time complexity will be O of n. Suppose out of this, one of the time complexity would have been O of n square. Correct. So the time complexity here, suppose this is, so in that case it will be 0 1 plus n square plus 1. Correct. So O constants will be again removed, it will be n square plus n, right? Again you see here, no, compared to n square, n is a smaller value, right? So our main focus should be on the bigger values, because this becomes negligible in front of this one. So our total time complexity will be O of n square only. Getting it? So that's how the time and space complexity is calculated for any given code. Basically time complexity, some tips and tricks I gave you here, which you can use to calculate. No, simply by just looking at the code, you can make out what is the time complexity for that given code. There are other methods also like Master's theorem, which is properly used for finding the time and space complexity, but that's a time-taking procedure. It's for a full, process or steps which you have to follow. But these tips and tricks will help you quickly find out or verify the time and space complexity of your given code.
Now let's talk about searching algorithm. And the first searching algorithm that we are going to talk about is linear search algorithm. So what is linear search? It helps us to search an element in a linear data structure. Now let's talk about one example wherein we will be searching some element inside the array. So let's suppose this is an array and the elements are 10, 20, 30, 40 and 50. Now if we are trying to search an element that is 50 inside this array, how linear search works is that it checks each and every element that is to be searched, right? That is there in the element array, right? Let's talk about this example here, 50. Now 50 will be compared, right? We'll check, is this 10 equal to 50? No. Is this 20 equal to 50? No. Is this 50 equal to 30? Is this equal to 40? Is this equal to 50? Yes. So here we were able to do a linear search, right? We were searching for this element inside this array one by one. We compared first it with 10, then 20, then 30, and then 40, and finally then with 50. At the end, we were able to find this element in the array in a linear fashion. Now, this is what is termed as linear search. Now let's talk about linear search algorithm. Since it is a very straightforward, or you can say a brute force algorithm, right? It's a brute force algorithm of finding the element in the array. So this is how it works, right? We have one for loop wherein we will be what iterating through all the elements, that is from 0 to n, and inside that what are we doing? We are looking for the item, that is that element that we want to search, right? Let's suppose this is 50, right? This 50 will be, we were checking if this 50 is equal to the element that is ARR of I, right? And then if that is the case, if we find out the element in the entire array, we will return its index, right? That is index, right? That I, we will return this I. Now there might be the case as well if we are at the end of the array and we have exhausted the last element as well and we were not able to find this 50, right? Let's suppose this is 10, 20, 30 and 40. Now this 50 is not present in the entire array. At that time, what we are going to return is -1. So we will say that, okay, we were not able to find this element whenever we are returning this -1 in this array. And this -1 indicates that we were not able to find that element.
Now let's see the implementation of linear search algorithm. I'll go directly to the Eclipse IDE and will start writing the code. So here I have created the class search, and then there is a public static void main method. Now inside this we'll be writing the concept or the logic for search. So as you saw already, what is the logic behind the linear search, and that is that you have to linearly search each and every element in a given array one by one, starting from the 0th index. Okay, here I'm using array. You can use any other data structure also to perform linear search on it. But linear search concept is always that you have to start from the beginning and one by one keep on searching till the end. Fine. So let's see its implementation. So for that, first I'll create a array, okay, which we are going to search. New int, and I'll define the array itself over here. Maybe 6, 4, 5, 8, 2, 1, 9. Okay. So this is the array defined. Now let's perform linear search on this. So we'll take the user input, that which element the user wants to search or which the integer value among the given the user is looking for or searching for. So for that, to take the input, we use scanner class in Java. So scanner s1 is equals to new scanner, and in the bracket we pass as a parameter the input stream. So system.in represents that I'm going to provide input through keyboard. For this I have to, I think, import the class. Yeah. So scanner class has to be imported. Now we'll take the user input. So let's put a comment also here. enter the element to be searched. Okay. Now we'll take the user input. So int maybe key is equal to s1 dot. So you can see here next int is a method which is used. So we'll use it directly here. Done. Now comes the main logic of the search, linear search. Okay. In that we'll run a for loop that will begin from the beginning of an array and will go till the end of the array. And at every index we have to compare that the value at that index, is it equal to the key that is being searched. If it is equal, then that index should be returned as an output. If it's not, then it should say that the number doesn't exist which you are looking for. Okay. So that's the whole logic. Let's write a code for it. So as I said, we'll be using for loop for int I equals to 0. I should be less than what? A1 dot length. So A1 dot length gives the total length of the array, whatever is its length. So in this case, it will give you 1, 2, 3, 4, 5, 6, 7. 7 as an output. And then I plus plus. This for loop, what do you have to do? Compare. So again, for comparison, you have to use if loop A1 at ith index, is it that equal to the key which we are searching? If it's equal, then what should be done? If it's equal, then we should print first of all element is at index I, right? That's it. Okay, what will happen if the element doesn't exist in the complete array? What has to be done for that? Okay, here there should be this. Okay, as it is a string, it should be in double quotes. So yeah, so what should be the case when there is no element, that element being searched is not there in the array? So in that case, let's use a logic here. What I'll do is I'll initialize one variable that is maybe count is equal to initially 0, and every time when it is, if it founds any number, it will increment itself. Okay, so count will be 1 now. And if suppose it doesn't find that particular element in the complete array and the complete for loop runs, so count will remain 0 because it will only increment if this if loop is true, and if loop will be true only if condition will be true. So if condition will be true only if any given element in the array is equal to the key which you are looking for, right? Until unless count will remain 0. So that's what the logic I'm going to use. So after this, I'll write that if count is equal to 0, then in that case should print that element not found in the given array. Fine. That's it. So that is the simple logic behind your linear search. Now let's see. When we run this program, it asks the element to be searched. So these are the elements 6458219. So out of this, suppose I give as the 8 as an input. Okay. So it says, okay, one second. Element not found in the given array is also being printed, and the output is also being printed. So let's see, something is the mistake. I think this closing of the loops. Yeah. This should be outside the for loop. Okay. The for loop ends here. So outside this, it should be. Now let's run. Check if it gives the correct output. So yeah, you can see 8 is the element entered. So it says element is at index 3. 0, 1, 2, 3. So yeah, at the third index, 8 is present there. Right? If I enter some, look, like I'll run the program again. If I enter some value, suppose 78. 78 is not there in the array. It should say element not found in the given array. So that's the simple logic behind your linear search. So we saw the implementation of linear search in Java programming.
Now let's talk about the time complexity of linear search. Now, if you observe carefully, let's try to understand this best case, right? So now if you are looking for the element, and let's suppose these are the elements in the array. Now Let's suppose in best case, what can happen? You're looking for 10 and 10 is the first element in the array. Now, how many iteration did you require? Did it require to find the 10? None, right? The constant time, right? Only one single unit operation was done and you were able to find this 10. So this is the best case time complexity where the element that you're trying to find is the first element that you search, right? In this case, you are looking for 10 and 10 is the first element. So this is your best case. Now, what about the average case and the worst case? Now, let's suppose average case is that you were looking for an element which is at the middle point, right? Let me just see. 0, 1, 2, 3, 4. Now, or you can put another and looking for 60. Now, in this case, or you can just skip it, okay? No need to add one more. Okay, so now you're looking for an element which is somewhere around in the middle. Okay, in this case you're looking for 30. Okay, so now if you observe, you are only iterating half of the elements, that is 5 by 2, which is nothing by n by 2, since constants doesn't play in do not play any role when you're talking about time complexity. So that is why average case still boils down to big O of n. Now, what happens in worst case? You're looking for an element that is 50 and which is present at the end of the array. Or in the worst case, you're looking for something that is not present in the array. That is 60, let's suppose. And in that case, you will still iterate through the entire array. And that is why the worst case time complexity in that case will be big O of n, because you are iterating through the entire array and that element was not found. You're looking for 60 and that is not present there. So you're iterating through the entire array, that is n operations are done. So that is why it boils down to big O of n. Now let's talk about the space complexity of linear search. When we are trying to find the element in the array, that is 10, 20, 30, and 40 and 50, we were not using any extra memory, right? We were not using any auxiliary memory, that is what we mean by auxiliary memory or extra memory, in order to find that element. We were just looping around these elements one by one, and we were doing it on this particular, on the same array that we were given, right? Since we are not using any auxiliary memory, that can be in the form of what? A stack, a linked list, or an array, or a string, or a queue. We are not using these auxiliary memories because they are not required, right? We are searching for an element in this particular array that was given to us, right? So the space complexity of linear search is constant, right? We were able to find it in a constant amount of space. Okay, we are not using any extra space. Now let's try to understand binary search algorithm. What is binary search? So binary search is one of the searching techniques, right? Like we saw in linear search, wherein the time complexity of linear search was big O of n, right? We were iterating through all the elements, and now this is a much more efficient algorithm as compared to linear search. Now again, why do we need searching is the thing that, let's suppose if you have a given set of elements and you want to search if that element is present in your array or not, that time, right, we can use either linear search or binary search. Now binary search is much more efficient and it is used on a sorted array, or it can be used on an array wherein some order is maintained, because based on that order we will divide our array, right? It is a searching algorithm which is or which follows the divide and conquer strategy, right? Let's suppose this is our array, and now since it will be divided in such a way that we can neglect one part of it, right? We will be dividing and then conquering. That means we will be then searching for our element. Now, let's suppose we are looking for something that is, now let's take an example wherein this array is written or the elements contained in this array are in such a way that if we skip this part, or the left hand side will be skipped, or the right hand sides can be skipped in such a way that they don't affect our output. So every time in linear search, our search space is reduced unless and until we find that element, or the array is exhausted. Okay, so our search space is reduced to half in every iteration. So this is what a binary search is. We'll look for an element in such a way that every time we are neglecting half portion of the array. And let's take an example. When we have this entire array, so first half, that means if if there are 8 elements, 4 on this side, 4 on this side, these 4 will be neglected. Then we have 2 on this side, 2 on this side, these 2 will be neglected. Then 1 on this side, 1 on this side, then this one will be neglected unless and until we find that element or the entire array is exhausted, right? So this is how your binary search works. Now let's try to understand binary search algorithm. So first we are going to understand the iterative approach, and then we are going to understand the recursive approach. So iterative, as the name suggests, we are going to use for loops, right? We will start with a for loop, and it will iterate, and we will iterate unless and until the beginning is less than the end, right? So because we will be updating our both beginning in some cases, and in some cases we'll update our end. Now, what happens? Now, since we know that in this iterative approach or in this binary search, it doesn't depend whether we are using iterative approach or recursive approach, the logic will remain same, right? So we will be having this array, and it will be in some order so that we can neglect some part of it. It doesn't have to be sorted always. We can still apply binary search even if the array is not sorted, but still some order is there so that we can neglect some part of it. Because again, keeping this thing in mind, that it follows the paradigm of divide and conquer. So now we have this beginning and end at place, and we will always iterate when beginning is less than end, right? So now what happens after that? Now we have this array, and now what we will do, let me take new pointers. So this is your beginning and this is your end. So this is your beginning and this is your end. Now you will be taking a new middle index, right? M, let's call it M. And now let's name these things 0, 1, 2, 3, 4. So you will do what? Beginning plus end divided by 2, so that some part of it can be neglected, right? So it will be 2. So your mid is at this position. Now you will see, okay, the element that I'm looking for is, let's suppose, is 50, and the element that I am currently at is 30. So obviously it will be never from this side. There is no chance that we will be able to find 50 from this side, that is the left hand side, right? First we will check, okay, is this 30 equal to 50? No. So this will never be executed, right? Then we will check, is my item that is there, is this 30 less than or greater than 50? If it is greater than 50, right? If the element that is, if item that is 50 is greater than 30, right? Which is in this case, our 50, that is the element that we are looking for, the item is this point, is greater than 30. So there is no point that it will be on this side. So we will skip, or we will neglect this half portion of the array. So that is why our new beginning is updated. It will be new, it will be middle index plus 1, that is middle index was 2 plus 1, that is this will be our new beginning. So we have smartly skipped the half portion of the array. So now let's rub all of these things, and now let's see what happens in the next iteration. Now we'll keep this thing in mind, that we are not looping, or we are not exceeding this limit, that is beginning should be always less than, or it should be always less than or equal to end. Okay, so this condition should be maintained. And similarly we'll again divide our array and then look for the same things, right? First we'll look for the element, then we'll skip some part of it. So this is the iterative approach for binary search, right? Now let's look at the recursive approach or recursive algorithm for the same. So again, beginning, the ground rule will remain same. We'll always iterate, or we will always recursively call binary search unless and until this beginning is less than end. Done. Now what happens, we will again find middle index, that is beginning plus end divided by 2. Then we will look for the element. These three steps will remain same even if you're using recursive approaches. Now what happens in recursion, right? We again call the function again and again. That is what is recursion. So in this entire tutorial we will be covering recursion as well, but in the later part of the course. Here you can get a good intuition, or let me give you a brief intuition about how recursion works. So let's suppose this is your activation record. Every time when a recursion is there, an activation record is called. So let's suppose you have these three statements. And let's suppose in your algorithm you have statement p1, p2 and p3, right? And at p2 you are calling the function again, right? You're calling this function again. So now what happens, an activation record is called. He will check, okay, is this statement executed? Yes, so one will be executed. Is second executed? Yes, so second is executed. But at second you're calling this function again, so at that time again a new activation record is created. Now this third step is left behind, right? Now this will be covered when we come back or return from this function call that we called here. So let's suppose this function was here. Now in here you are returning, right? This function called, let's suppose this is not less than beginning. Beginning is not less than end. So this will be somewhat, this case is relatable, right? This is similar to what we are looking for, right? Let's suppose there is some similar situation wherein beginning is not less than end. At that time you will be returning from this. Right now, once you have returned, you will be then calling this function again, but this time around for this. And let's suppose this time around you are calling this one is executed, step one is executed. Now again this activation record is called, this activation record is one, and then again this is called, right? This is executed again, this two is called again, a new activation record will be created, and these three steps, the step third will be still left for execution. So now here you return, right? Then it will go back to this step, right? And then once you are done with this, now there are two positions or two possible scenarios where you can return. Either you are returning from this function just like we have executed this condition and we return, right? Another is that once you are done with this entire activation record, at that time you will also return. Okay, so these are two scenarios. Now you have executed this, there is no step to be executed, it will return. Now this was left behind, this will be executed. Now nothing is to be executed, it will go to the caller, which was this, and finally it will go to the main method wherein we call this at the first place, this function. Okay, so this is how an activation record is created, a stack is maintained. Okay, even if you might be thinking we are not using any extra space, but whenever recursion is there, an extra space that is in the form of stack, that stack is maintained. So you need to keep this thing in mind while you are playing around with space complexity at the time when you're using recursion. Okay, so now with that being said, let's clear our screen and let's see how recursion is called here. So again, now recursively what we will doing, if now we have this mid, right? And let's take an example of an array 0, 1, 2, 3 and 4, 10, 20, 30, 40 and 50. So middle index will be 0 plus 4 divided by 2, that is 2. So this is our middle index, right? So this is 0, this is our beginning and this is our end, right? So now we are hit here, right? So we again check the 50 that we are looking, this is our item that we are looking for. Okay, so is 50, and this is our middle index, is 30 greater than 50? No, it is not in this case, so this will never be executed. This is not executed as well, right? Now what about this condition, the else part? Now what we will be doing, we'll be skipping, since this 30 is less than, we'll be skipping this part and we will focus on middle index plus 1, which is nothing but this. So this will be our new beginning, and our process will start moving, right? So now again, then the same thing will happen unless and until this condition is false. Okay, so this is how your binary search works when you're using recursion. So now let's try to understand binary search and let's see its demonstration. Okay, so we are looking for 20 and this is our array, right? 10, 11, 16, 20 and 23. Now this array is sorted, right? So we can apply binary search. Okay, since we can neglect some part of the array based on some conditions. Okay, so now our beginning in the first iteration, what is happening, our beginning is 0, our end is 4 and our middle is this element. Now what we will be looking for is 16 equal to 20. No, it is not, but 16 is less than 20, so we will skip this part. In the next iteration, what happens, we'll be focusing on these three elements, right? That is 20, we will be focusing on this part, rather, if we say we'll focus on this part, right? Focus on this part. Okay, so now in the second iteration, what will be happening, our beginning is updated. Now our new beginning is this point, our end will remain at its own position. Now we'll find the middle index, so it will be 4 plus 3, that is 3, that is 7, right? And divided by 2, it is 3.5, right? So since this will be truncated, right, the truncation will happen and the integer that is there, the middle index will be 3. So this is our middle index, right? So you can see middle index is 3. Now, is this an element that we're looking for? Yes. So we'll return the index. So we found our element at index 3 and hence we return 3. Because if you observe carefully, it is returning, if the element is found, it is returning the index. So this will be returned. Okay. So this is how binary search works.
Now let's see the implementation of binary search algorithm in Java programming. So I'll directly go to the Eclipse IDE and we'll type the code there. So yeah, I'm already here on Eclipse IDE and I've created a file which is having a class named as search, and then public static void main method is also created. Now let's create a function for binary search and we'll call that function of binary search from the main method on a given array. So to create a method, public static void, not void, it's going to return the index which is found wherever the element is found. So binary search is nothing but it's a searching algorithm, right? And we have to search for a given key in any given array. And if it is found, it returns the index. If it doesn't found, then it says that the element is not found. So it will return int, that is the integer, the value of an index where the particular value is found in the array. So int, let the name be binary search. And it takes, what all it takes as a parameter. So it takes the array as a parameter. Okay. 1 second. Yeah, it will be A1. So first it takes an array integer, in which you have to search for the given number. And then it takes the value which will be searched by us, right? So it may be an int value, as it is an integer array. So let's have that the user is searching for an integer number. So let it be a key. And then to implement binary search algorithm, we need the first starting index and the last, that is the ending index of a given array. So that has to be given as a parameter here in this function of binary search. So int first and int last. Okay. Okay, so it's giving an error saying that you have to add a return method. So need not worry, as when we'll add return method, that error will definitely not be highlighted over here. Now, what's the logic of binary search? So binary search does what? As the name itself says, binary, meaning half. It divides into two halves. From the mid of the given array, it divides the array into two halves. Okay. The first, from starting from first index to the mid is one array, and from mid to the last is another array. And then it searches in the respective half. Like for example, the element which you're searching for is greater than the element in the mid. Then it will search the second half. If the number you're searching for is smaller than the middle element, then it searches the lower half. That's the logic behind binary search. Let's write that. So what will happen, that Okay, if will come later. First we'll write int mid. We'll find the middle element. Then only we can divide into two halves, right? So middle element will be first plus last divided by 2. Right? Let's put this in brackets. Okay. Middle element found. Now let's divide it. So for that we have to put a condition first. First condition is that always the search should be between the given range of an array. That is between first and last. Correct? You should not go on like searching, like suppose the arrays are stored from index 0 to 10 and there's no point searching after the index 10, right? Or before like 0, that -1, -2. Correct? So which the first condition is that is first should be less than equal to last. Okay. Now inside this condition all other conditions will come. Now that what is that condition? If suppose the given key is found at the mid of the value, like it is dividing from mid, like the numbers, if the number is lesser than the mid value, then it will search the lower half, greater then it will search the upper half. But what if it is equal to the mid value itself? That also has to be checked. So if key is equal to mid, then in that case it will just return that particular index, that is mid. Okay, it will be a closing here. Okay, now if it is not at the mid, then what has to be done? Then if the key is less than the mid value, then in that case what has to be done is go to the or implement the binary search again on the lower half of the complete array. So you have to return from here what? Binary search. That is, you have to call the method again. It's a recursive call to the same function. And here you will pass the array itself, A1, and then you will pass the key. Now what will be the first element? First will remain first, but end will become the one value lesser than the mid minus 1. Right? Then it comes as else. You have to return what? Binary search and implement on the given array A1. Input will be the key. In this case, your last will remain the same, but your first will change one value more than mid because the second half is being searched now. So mid plus 1 will be your first and last will remain your last. Getting it? Semicolon. Okay, we'll see what's the error here. Unreachable code. Okay. Let's fix this. So mid is here. Okay, this is opening here, closing over here. This is closing, correct. This is closing over here. Correct. Okay, let's close this over here. Okay, so so it is closing over here. Now, what if the element is not found at all? It gets searched everywhere and still it's not found. Then in that case, it should return -1. Fine. Now let's go to the main method and call this function. So for that, first we'll create an array itself. A1 equal to new int. I'll define the values also over here. Let's take some random values: 4, 6, 2, 9, 1, 7. Okay. And let's call the binary search as a function, right? So let's call this. It will store the value in the index. Binary search. And I'll call over A1. The key I'm searching for, I'm giving it manually here. Suppose I'm looking for 6. The first will be your 0. First index is 0 in the array and the last index is array length -1, because length starts counting from 1. So 1, 2, 3, 4, 5, 6 will be the value. But actually the index starts from 0. So it will be 1 less than 6, right? 0, 1, 2, 3, 4, 5. So it will be A1 dot length -1. Okay. Then we can put a statement here saying that if your index value is equal to -1, then in that case, it should print that element not found in the given array. Okay. Else it should say element found at index plus index. Okay. Let's run the code. So I'm searching for 6. 6 is there in the array, right? So it would say the, okay, cancel it. There's some error is what it's showing. Okay. So there will be a semicolon. Right. Let's run the code. So it says the element not found in the given array. So I'm looking for 6, but it's not being found. So it's returning -1. Okay, what's the error? Let's try to fix it up. This is A1 dot 0. This is A1 dot length -1. 2. Okay, we'll see here. Some issue with this, I guess. Yeah, so I looked at the error, and what I could see here is that if we change the numbers here, that is the elements of the array, to be in ascending order or in sorted order basically, because the first requirement of implementing binary search is that the element given should be in a sorted order. Okay, because then only you can compare that from the middle element. If the key is greater, then it should be in the later half, that is second half. And from the center element, if the key being searched is smaller in value, then it should be in first half. And that comparison is only possible if it is in a sorted order. So that's the only change I did here, is that change the values of the array, that is the elements in the array. And then let's try to execute it with, suppose I'm searching for 3. Okay, here I'm hard coding it with the key which was being searched. This is 3 over here. So let's run this code and check. So you can see here it says that the element 3 is found at index 1, starting from 0. So 0, 1. You can check for any other. So maybe 6. Also, if we check, so we'll get that it is at index 3. So 0, 1, 2, 3. So that's how the binary search works. If suppose I'm checking for something which is not there, then it should say that the element not found in the given array. Okay, so that's all about your binary search and the implementation of binary search in Java programming.
Now let's talk about the time complexity of binary search. Now, in the best case, now what is the best case? Now let's take an array, and in that array, 1, 2, 3, 4, and 5. These are the elements. Now, the best case is that not that if the element, like we saw in linear search, this element, when we are looking to search for this same element, at that time that was the best case scenario for linear search, right? But in this binary search, the best case scenario is when your middle index is at this location, and you're searching 3 in the entire array. So at that time, this will take a constant amount of time, and this is the best case time complexity in that case. Okay, now in average case, what happens, right? If you talk about this algorithm, let me just clear out my screen. So it follows a paradigm of divide and conquer. So let's suppose you have 8 elements first in the array. It will be divided into 4, because these 4, or either it can be on the left side or on the right side, will be neglected. And then we deal about these, then we focus on these things. Okay, these 4 elements. Again, it will be divided into 2 and 2. Then we will neglect 2 elements. Then 1 and 1. Then again, there will be one of the element can be neglected. So there are 1 and 1. So we focus on this element. So the entire operation will be done, or entire searching will be done in 3 steps, right? Now, if I take an example, and if I do a log 8 to the base 2, what should be the value of this? Obviously, when I do this, this can be written as 2 raised power 3, right? And this can be written as 3 into log 2 to the base 2. Now this is 1, and now you get the answer as 3. So this 3 and this 3 are equal. That means if I talk about the worst case time complexity of binary search, it will be somewhere around log n. As we saw in 3 steps, we were able to find the element, and the log n, that means log 8, is the answer of that is also 3. So you get the point, right? So the worst case time complexity of binary search is log n, and same goes for the average case, wherein it will be somewhere around log n divided by 2, neglecting log n divided by 2, neglecting the constant terms. It will be again, or it boils down to big O of log n. Okay. Now let's talk about space complexity of binary search. Now, when you talk about space complexity, right, we only think of auxiliary memories, or you can say that what any extra memory that you guys have used. Since we did not use any extra memory, that can be in the form of array, or it can be in the form of stack, or it can be in the form of queue, or linked list, or even strings, right? Since we never use these extra memories in our implementation, so the space complexity of binary search is big O of 1. That is, it takes a constant amount of space.
So now let's talk about what is greedy programming, that is introduction to greedy programming. So what is greedy approach to programming? The name itself makes it very clear, that is greedy, meaning when you are greedy about the optimal solution. So greedy programming helps you reach to an optimal solution for any given problem. Why? It helps you reach to the optimal solution because greedy programming follows an approach, that is, it helps or it finds the optimal solution locally, which ultimately leads to a feasible solution. It is a step-by-step process in which at the very first step, the most feasible as well as the optimal solution is selected. Then we move to the next step of the solution. And then there also the most feasible, optimal and feasible solution is selected. Then we move to the next step. Similarly, going forward, we reach to the final step and finally we obtain a feasible and the optimal solution. It might be the case that in some cases we might not obtain the overall optimal solution, but definitely it will be a feasible solution. Okay, and also the advantage of using greedy programming is that may the solution of a given problem is not optimal overall, but locally it would be the best solution possible. For example, if I consider that I have to go from Bangalore to Delhi, okay, and on the way, the restriction is that I should either go via Mumbai or I should go via Hyderabad. Okay, and the final question to this scenario is that you have to find out that path which takes less time to reach from Bangalore to Delhi. Suppose to reach from Bangalore to Mumbai and Mumbai to Delhi, similarly from Bangalore to Hyderabad, Mumbai to Hyderabad and Hyderabad to Delhi. The time taken to go from Bangalore to Mumbai is, 2 hours. Suppose, let's assume, from Mumbai to Delhi, suppose the number of hours is 4. From Bangalore to Hyderabad, the time taken is 3. From Hyderabad to Delhi, the time taken to reach is 2. Then from Mumbai to Hyderabad, the time taken to reach is 6. Okay? Now, what will greedy approach to this problem will be? So you have to find out the optimal path, right? As well as the feasible path. So what will be done is in greedy approach, you'll start from one location, that is from Bangalore to Delhi. If you have to travel, you will start from Bangalore. And locally, that is in these two, there are 2 paths to go out from Bangalore, right? One is this way and one is this way. So among the both path, it will find out which takes less time, because that's our question statement is. That is, you have to find out the path from Bangalore to Delhi, which takes less time. So locally it will try to find which takes less time among 2 and 3. So 2 takes less time, right? So it will take this path as its solution and go to Mumbai. From Mumbai, it has further 2 more paths. One is taking 6 hours of time, another is taking 4 hours of time, which is less in these two, 4 hours of time. So it will take this path because it is greedy of the optimal solution. It's greedy of the feasible and optimal solution in the greedy approach. So Mumbai to Delhi, this takes only 4 hours of time, so it will pick this 4. So it will give the solution that to reach from Bangalore to Delhi, this is the path to be followed, that is via Mumbai, and it takes 6 hours of time. But if you see here, to go via Hyderabad, it takes less time. That is only 5 hours. But greedy approach find out a solution to go from Bangalore to Delhi via Mumbai, not via Hyderabad. But you can see locally, if I consider that, okay, if between Bangalore to Mumbai, which is the optimal path, then definitely this is the optimal path. And between Mumbai to Delhi also, the optimal path is this only. If we go via Hyderabad, it takes 6 plus 2, 8 hours of time. So locally, it is the best solution. But overall, this approach didn't give the best solution. But there are certain situations, certain problem statements whose solution using greedy approach only gives you the overall as well as the local best solution. Okay, so I hope you have understood what greedy approach to programming is all about. Now let's talk about the different examples of greedy programming. So there are various problems, the computation statements which are solved with the help of greedy programming. Okay, the examples here I have listed few, there are many such. And any new problem can also be solved using greedy programming. So example here is the first one is your traveling salesman problem. So traveling salesman problem is kind of a problem where a salesman has to visit every city in a cluster or in a group exactly once and return back to the original city or the original place. And the best route is found here. And the problem here to find the best route is obtained by solving it with the help of greedy programming. Okay. Similarly, Prim's minimal spanning tree algorithm. So finding out the spanning tree which has a total minimum weight is done using two approach. One is Prim's and another one is Kruskal's. And both of these approach follows greedy programming. The next is Dijkstra's algorithm. So Dijkstra's algorithm is a single source shortest path for a graph. So in a graph, if you have to find the shortest path from one vertex to all other vertices, then we use this Dijkstra's algorithm. And the solution of this problem of this Dijkstra's algorithm, the basic underlying concept is on greedy programming. Similarly, graph vertex cover. So graph vertex cover is set of those vertices in a graph such that in that set, at least one vertex covers one endpoint of all the edges in the graph. Okay, so set of those vertices which covers at least one endpoint of each edge in a graph comes under vertex cover. And solution to this, like that is finding the vertex cover, the basic concept is also behind greedy programming. Similarly, knapsack problem, where knapsack problem is about selecting the items with certain weight into it such that the total sum or the total profit is maximized and the total weight being carried is minimized. Okay, so all these problems I said is solved using greedy programming. That doesn't mean that you cannot use any other approach for solving these problems. You can use, but using greedy programming, these problems gives the most feasible and optimal solution. Okay, so I hope you understood the examples that are under greedy programming. Now let us talk about greedy programming versus dynamic programming. That is, the difference between greedy programming and dynamic programming is what I'm going to discuss now. So talking about greedy programming follows an approach where it looks for the near optimal solution. Okay, the local optimal solution, the local best solution. But dynamic programming looks for overall optimal solution, overall best solution. Okay, so this is the one major difference. Next difference is in the approach. That is the approach followed for greedy programming and approach followed for dynamic programming. And that difference is that in greedy programming, the previously selected sub-solution is not taken into account into the present scenario. But in dynamic programming, the previous subproblem solution is taken into consideration in order to find the current best solution. Okay, suppose there are 5 steps in solving a problem. So in those 5 steps in greedy programming, the approach will be that the first step solution will be found, then second step best solution will be found, then third step best solution will be found without considering the previous step solutions. And then finally at the fifth step, whatever is the best solution, that becomes your final solution in greedy programming. But in dynamic programming, first step of the problem is solved. Moving to the second step, then what was the solution in the first step is considered in finding the solution at the second step also. Similarly, moving to the third step, the solutions which were obtained, or you can say the sub-solutions which were obtained at step first and second, is again considered at step 3 also. Similarly, going forward. So at the last step, all the previous solutions or sub-solutions which were obtained will be considered, and then final solution which will be given. And that's the reason in dynamic programming, the optimal solution is obtained, the overall optimal solution. Okay. Second difference is that in greedy programming, the overall optimal solution may or may not be obtained. But in dynamic programming, it's always the case that the overall best or optimal solution will be obtained. In greedy programming, all the local solutions for a big subproblem, if I divide the subproblem into parts, then those individual parts solutions will be definitely the best. But in dynamic programming, if I divide a problem into subproblems, then individual subproblem solution may not be the best. Okay. So these are the difference. Again, another difference can be that in greedy programming, there is no much memory utilization, because in greedy programming, only the current step is focused. The previous steps of the solutions are not focused. But in dynamic programming, to find the current best solution, the previous found solutions are also considered. So you need to memorize the previous solutions, right? So it takes more memory to implement. And as dynamic programming considers all the previous steps solutions to find the current best solution, it is relatively slow. Greedy programming is relatively faster because it doesn't take into consideration all the previous subproblem solutions obtained. It only considers the current best scenario. Okay, so these are the differences between greedy programming and dynamic programming. Now, lastly, I will give us example, and with the help of same example, I'll explain you what is the difference between greedy and dynamic programming. So if you consider that this is the starting point, suppose this is Bangalore city, and you have to reach to Delhi, and you have to go via Mumbai, or you can go via Hyderabad. Okay. Similarly, this will be the other side for dynamic programming, the same problem I'm considering. Okay. So to go from Bangalore to Delhi, there are two routes here. You have to find out which is the best route, meaning which takes less time. Okay. Suppose to go from Bangalore to Mumbai, it takes 2 hours. Then to go from Mumbai to Delhi, it takes, to go from Bangalore to Hyderabad first, right? It takes 3 hours. And to go from Hyderabad to Delhi, it takes 5 hours. And to go from Mumbai to Delhi, it takes 7 hours. Okay. So in greedy programming, what will happen is that if I start from Bangalore, I'll look for the local best solution. That is, in these two, which is the less time taking? 2. So yeah, in these two paths, this is the best solution. So I'll follow this path. Then I have reached here. Now I will not look back, okay, in greedy programming. From here, what is the best solution? There is only one path to go to Delhi. So definitely you'll be following that path. Getting it? So this is the best solution found with greedy. Now coming to the dynamic approach. Same values I'm going to take here. I'm not going to change the value so that you can understand exactly the difference. And then here, 5 units, 5 hours. So in dynamic approach, what will happen? So you can see here that in greedy approach first, 7 plus 2. So it took 9 hours to reach to Delhi from Bangalore. But there was another best solution also. 5, 6, 7, 8. 5 plus 3, 8. So 8 hours was also a solution, which was actually the best solution overall. But in greedy approach, we didn't found that. In dynamic approach, what will happen? It will start from Bangalore. It will look for the best solution. Okay. Which is the best solution in these two? This definitely. It is taking less time. So 2 hours. Now after reaching Mumbai, it will also consider the previous steps. So it is knowing that, okay, we have left this path also. We should consider this path as well. So to go from Mumbai to Delhi, it will consider this path, okay? So 7 hours is taking here. So 7 plus 2, it is taking 9 hours, right? But dynamic programming also will consider the previous subproblem solutions, right? So it will say, check now that, okay, if I would have taken this path, that is 3 plus 5, then what was the total time taken? It was less, that is 8. So dynamic programming will finally give this path as the solution, okay? Not this path, right? So this was the major difference with the example we saw between greedy programming and dynamic programming. Now let's see what is fractional knapsack problem. So fractional knapsack problem is one of the application of greedy programming itself. That is, this fractional knapsack problem is solved using greedy programming. There are two categories of knapsack problem. One is your 0-1 knapsack problem. The other one is fractional knapsack problem. Okay, 0-1 knapsack problem gives the best solution when it is solved using dynamic programming. But fractional knapsack problem gives the best solution when it is solved using greedy programming. So that's the reason I have taken here fractional knapsack problem as one of the application of greedy programming. So what is knapsack problem first? In knapsack problem, what we consider is, so knapsack literal meaning is a sack, okay? So the scenario here in the knapsack problem is that there are certain collection of items. Each item is having an associated weight and associated cost. You can refer cost to be as profit also. Right? Now you have to determine those collection of items. You have to select those items from that whole lot or a collection such that the total weight is always less and total cost or profit is always higher. Fine. So the problem here is that if I consider just weight, that is, I have to select those items from the collection which has less weight, then I will not reach to the most optimal solution. But if I consider just profit, then also I will not reach to the most optimal solution. So you have to consider both weight and cost here, and such that the weight should be always as less as possible and profit should be as more as possible. Now, many such cases where there is no resource allocation done in industries or in any real life scenarios, it becomes a knapsack problem. Few examples are, first one is finding a way to cut raw materials in the least wasteful way. Also, you can refer it as cutting stock problems. So I'll tell you what this cutting stock problem is, that suppose in any industry, when the raw material comes, right, we have to cut that raw material into pieces. For example, cloth. So cloth has to be cut into pieces, or suppose any kind of a sheet, any metal sheet. So a person comes to buy a metal sheet, it has to be cut it into pieces. Similarly, if suppose that raw material is being used in manufacturing, cloth is being used in some other product manufacturing, then to meet that product manufacturing needs, you have to cut the cloth or the sheet or any raw material into certain pieces. So problem here is that you have to cut those pieces, raw materials, in such a size, such a length and breadth that least or less resource raw material is wasted. Right? And less resource is wasted and your needs are maximized. Your needs are fulfilled. So this is nothing but a knapsack problem, where you have to consider two parameters to reach to a most optimal solution, where one parameter should be reduced and the other parameter should be maximum. Okay, so similarly in cutting stock problem also, which I explained right now, this is the scenario. So any such problem in the real scenario can be applied or solved with the help of the solution which we have for knapsack problem. Now, what is knapsack problem basically? So knapsack problem is built behind a story, and that story is that there is a thief who wants to rob a store. Okay, he wants to do robbery in a store, and definitely the intention of the thief would be to carry those items which are less heavy to carry and would give more profit to him once sold, right? So two parameters are here also to be considered. One is your less weight, and the second one is more profit, more cost. So definitely it is a knapsack problem. Okay. So suppose there are n items available in the store, then the weight of each item will be represented with W of I, where I represent ith item, and its cost is represented C of I, where I represents again ith item. Okay. Now, to solve this problem I told you. Now to solve this problem, what items can the thief carry away? How to find out that? So obviously the objective of the thief is to carry the maximum profit items. But if he just considers the profit, he might end up carrying the items with more weight, right? And there is a constraint to it as well, that the size of the knapsack, the size of the sack in which he is going to put those items and carry away is less, or is having a fixed value. Suppose the size of the bag or the sack which he is using is of maximum weight of W. So he cannot carry more weight than this. So that is also one constraint here. So definitely he cannot just consider the weight or just consider the profit or the cost. He has to consider both the parameters. Now, even though he considered both the parameters, suppose there are, 1, 2, 3, these 3 items are there. Now, thief picked this first item. Okay, he put it in the bag. He put the second item also and put it in the bag. So the total bag now is occupied with these two. After these two occupancy, if he tries to put this item also in the bag, he's not able to, because the space which is left now in bag is less than this one. So what he should do? He should discard this and just pick these two items with him and run away. This is called as your 0-1 knapsack. Okay, meaning either the item is selected or the item is rejected. There is no third option. Next scenario can be that, okay, first item is put in the bag by the thief, second item is also put in the bag by the thief. While putting the third item, as it was not completely included in the bag, he cannot include it completely in the bag. He can take fraction of it. If suppose 2 kg is left, space is left, he can just take 2 kg part of it and put in the bag. He can break it into pieces and select that piece which fits into his bag. And this is called as your fractional knapsack. Okay, so 0-1 knapsack, either the item is selected or not. Either it's true or false. Getting it? So 0 or 1. Fractional knapsack, even the fraction part, even the pieces of that element can be selected if the full item cannot be selected. Okay, so this is your fractional. Now, let us understand fractional knapsack in more detail. The thief can select the whole items and the fractional part of one item. So what is fractional knapsack? As the name itself says, fractional, meaning while selecting the elements or items, fraction part of it, meaning pieces of it, can also be selected. Okay, if I put it in a mathematical way, suppose the selection here is first item, second item, third and fourth item. 4 items are there in the shop. Weight of ith item is Wi. So suppose this item has some weight assigned to it, 2 kg. This has 3 kg weight. This has 1 kg weight. This has again 2 kg weight. Okay. Next step is profit of ith item is Pi. Suppose this is weight. Suppose the profit of these items are this is having 20 rupee profit, maybe 30 rupees profit, 10 rupees profit, and 20 rupees profit. Next, the total capacity of the knapsack is W. So the total capacity of the bag which the thief is carrying or has to carry away with him is having some capacity, that is your W. Let the value of the W be 5 kgs. In fractional knapsack, he can carry the n of ith value of ith element. For any element, the fractional part can also be considered. Now, suppose the weight is 5, right? So the maximum profit which gives us this one, 30, right? So if he considers this 3 kg, so suppose he took this 3 kg. I'm not following any algorithm here, just to explain what is fractional knapsack. Suppose the first item considered is 2 and it is having 3 kg weight. Okay, 3 kg is took. Now only 2 kg space is left. So either he can select this or this. Anyone he selects, he'll be having 20 kg of profit. So he'll select this 2. Now his space is fully occupied, no space is left there, and he went away with these two items, 2 and 1. 3 kg plus 2 kg, 5 kg. Suppose the maximum capacity of this is 4. And the first item the thief selected is 2, second item. It is having 3 weight. Okay, done. Second item the thief selected is, suppose, the first item. But first item is having 2 as a weight and only space left in the bag of the thief is 1 kg. Right? So he cannot select this 2 completely. So what he'll do? He'll select half of it. That is 1 kg he will select, 1 kg he will leave it. So out of 2, he just selected half of it. That is one part of 2 is selected. Right? This is called as your fractional knapsack. Okay? So the constraints here are that weight should always be greater than 0 of each item. Profit definitely is a cost, so it should be greater than 0. The weight and profit both cannot be negative numbers. So that's the two constraints. The third constraint is that the fractional part should always be between 0 and 1. Right? Always the fraction will be between 0 and 1 itself. So that's the third constraint. Now, what is fractional knapsack algorithm? So let's see this fractional knapsack problem and its associated algorithm. So how will we solve this problem where both profit and weight should be considered? So the first step here is that find out the ratio of profit by weight. Okay, in this case, this way we'll consider profit and weight both. So to calculate profit by weight for each item. Next step is that you have to arrange this ratio obtained in the first step into the descending order. That is from maximum to minimum. Third step is that you have to start putting the items into the knapsack one by one from that item which has the maximum value of the ratio Pi by Wi. Wi represents weight of ith item, Pi represents profit of ith item. Okay. So in that one by one, you have to keep selecting in this descending order itself the elements, but you have to consider the total weight of the knapsack also. So you have to keep on selecting the elements until and unless you reach to the total weight that can be carried out by the, okay. So you have to always keep this in mind that the sum of the weights which you are picking up of the items should always be less than the total capacity of the knapsack. If the total capacity, the free capacity of the knapsack is less than the weight of the item, then the fractional part of the item can be selected depending upon how much capacity is left in the bag. Okay, and then finally the last part will be to calculate the final profit of the cost depending upon the items which has been finally selected in the bag. Okay, now for this fractional knapsack problem, let's see an example and try to understand how this algorithm is actually implemented. So there are these 5 items here, 1, 2, 3, 4, 5. Weight is given 5, 20. Suppose the weight is in kg and profit is in rupees. Fine. So the weight of all these 5 items, profit of all these 5 items is given, and also the total weight, the capacity of knapsack, the 60 kg is given. So the first step of the algorithm says that you have to find out the ratio of Pi by Wi, right? So profit is 20, weight is 5. So 20 by 5 would be 4. Then profit by weight, 30 by 20. It would be 3 by 2. Profit by weight is what we have to find, right? Similarly, third item, profit is 40, weight is 50. The final answer would be, after dividing these two, 5, 3, 8. So 3, 2, 6. This, let's convert this also. 3 by 2 is 1.5. Now this profit by weight, so 50 by 25, this is 2. Then 60 by 30, profit by weight. So this is also 2. Okay, this is your first step. Done. Second step is to arrange these items as per their descending order of their ratio of profit and weight. So descending meaning the highest is your 4, and this is for item 1. So 4 for item 1. Next is your 2.6 for item 3. 2.6 for item 3. Next is your 2. So these both are 2. So anyone can be considered, no issues. So 2, okay, for fourth item. Then 2 for fifth item. The last one is 1.5 for second item. So this is your second step. Third step is you have to select these items now one by one from the beginning. Okay. So the first item to be selected will be this one. Okay. So now here comes the consideration of total weight, that is 60 kg. Fine. So first I'll be selecting the first item. So first item is selected. It is having weight as 5. So 5, initially the bag is empty, right? So the value of, initially the value of W is 0. Now 5 kg is selected. So now the weight value will be 0 plus 5, right? That is 5 kg. Still 5 is less than 60. So we'll compare that is 5 less than 60. So yes, it is less. So we will select the next item. That is your third item. So third item is having weight as 15. Okay. You have to select in this order only. The third item is having the weight of 15. So okay, 15, third item will be selected. Now the total weight is, earlier it was 5, now it is 5 plus 15. So 20. So 20 kg already is selected. Still 20 is less than 60. So we'll proceed ahead. Next element to select is fourth element, which is having weight as 25. So 20 plus, okay, 25 is selected. So now new weight is your 20 plus 25, which is your 45. Fine. So still 45 is less than 60. So I can select more items. Okay. So the next item to be selected now is fifth one, which is having weight as 30. So if I select 30, and weight will be your 45 plus 30, which is your 75. It means I cannot select this. 75 is greater than 60, meaning the capacity of the bag is less than the total weight. So I cannot consider this. So in that case, what you have to do is select the fractional part of it. Meaning, if you cannot select the full, you'll select some part of it. How to decide which part of it? So you can see here that after 45, the space left was 60 minus 45. That is 15. 15 kg space is only left. And the weight of this is 30 kg. So you have to select only 15 kg out of 30 kg. Meaning 2. That is half of the weight you have to select. So if you select half of the weight, then your 60 kg weight will be completed. Right? So no more further selection has to be done. This is your step 3. Now the next step, or you can say the last step, is your calculating the profit. So how will you calculate profit? Depending upon which all weights you considered, which all items were picked. So first item was picked, which is having 20 as the profit. So once the final weights or the items being selected is decided, we can go ahead and select and find out the final profit obtained. Okay, so these are the items selected. So first item was selected having the profit of 20 rupees. Third item was selected, which is having a profit of 40. Then fourth item was selected, which was having the profit of 50. Then the fifth item was selected, which is having the profit as 60, but fifth item was not completely selected. So definitely profit will also be divided. Okay. So as we selected just half of the weight of the fifth item, the profit will also obtain will be half of it, right? So the weight which was selected, that is 15 kg was selected out of the available 30 kg. So 30 kg into the profit, that is your 60, right? So the total profit obtained was 20 plus 40 plus 50 plus 1 by 2 into 60. This is your 30. This is your 30. So the total answer would be 90 plus 20, 110 plus 30, 140. So the total profit here obtained is 140 rupees. So this is how we'll solve the fractional knapsack problem. Now let's see the fractional knapsack problem in Java codes. Okay, so I'll be going to the IDE and we'll type a code, write down the program for the algorithms understood just now. So let's go to the IDE. So here I have already created a class example with public static void main method inside it, and directly I'll go to writing the code for fractional knapsack problem. Okay, so let me first declare a few variables which I'll be needing in the entire code. So maybe I and j for the loops. Okay, let us initialize them, and then okay, one more will be the total capacity of the knapsack, right? So these two. Then there will be also the intermediate weight. For that we'll need, for storing the intermediate weight values, we need one variable, and then maybe the total number of elements. Let that, I'm hard coding it, the total number of elements to be 4. You can select the change here, or accordingly you can write the program, but let's make it simple. Next, I'm having the two floating point values, sum, which will be initialized to 0. Then also the ratio which will calculate between the profit and the weight. That will be your floating point, right? Let's not initialize it to anything. Done. Now I'm going to implement or include the weight and profit of each items in my code with the help of a 2-dimensional array, where there will be 2 rows. The first row will be having the weight, and second row will be having the profit or the cost. Okay, so let me define that as well. So int array, okay, 2-dimensional array, so 2 brackets, or let it be short name a1 equals to new int, 2 rows will be only there, and number of this will be 4 because 4 elements are there. Okay, now a1 0. So in the first row, what I'm going to have is all the weights of the elements. So let us initialize that also. I'm going to hard code that as well over here. Okay, insert any value, maybe 2, 4, 6, 8. Okay, next in the second row, that is of the array, we are going to have the profits. Okay, and let's store the values here also by hard coding it. 20, 40, 60, 80. Okay, then let us have the total capacity of this defined. So capacity is equal to maybe 6. Okay, take any value here. Now we have to start with the actual logic now. So after every step, we have to check that is the bag full or not, right? The intermediate weights have to be checked before selecting the new item. So that I'll store it into a variable m. Let it be initially as equal to the size of capacity of the bag. Right? Now, while there are more elements into it, meaning while m is greater than equal to 0, meaning until the full bag is full. So here m is the total size, that is 6. Okay, so it will keep on decreasing after I select every item, and when it reaches to 0, it means no more items can be selected. The bag is completely full. So that's what the condition is I've written here. Let the ratio be also initialized to 0. Now after that, we'll have a for loop to traverse each element. So I is equal to 0, I less than n, I plus plus. Okay. Then we'll check here if the ratio is, so to check if array, okay, A1 of 1 first row ith element divide by A1 profit was second one, so profit by weight, so 1 and then this will be 0, right? Ith element, this to be included together. Okay, we have to convert this to the floating point, right? So let's convert this to float. Okay, so float, this also should be converted to your floating point. Okay, now dividing this with the float and then checking that this should be greater than the ratio. Okay, if it is, then, so it's showing error, let's check, required boolean showing float. Okay, now it should not show, right? It's greater than ratio. Okay, let's proceed further and check. Then in that case, what has to be done? That ratio should be equal to this value itself. So I'll just copy paste from here. Float. Okay, this is extra, right? And j will become your I. This will also be closed. Now after that, if your again A1 0 j is greater than m, meaning if there is more space left, then you have to calculate the sum now. So sum is equal to sum plus m into ratio, right? Meaning you have to select the half part of it in ratio of it, not the full. And then m will be equal to minus 1. It will reduce 1, right? Now going to the else part, if you don't have to select the fraction part, then in that case, m will be equal to m minus a1 of the item being selected, right? Or j. And sum will be equal to sum plus floating point of the rate. Floating point of A1, 1 and j. Okay. Now A1 will be further reduced to 0. Okay. So after this, we have to now print system.out.println. We have to print the final profit is plus of sum. Okay, I hope this is clear why this is giving error. Let's see if float is closed here. This is closed here. Okay, so let's see the output of it. Are we getting any error or what's the output? So the answer is 60. Let's see if the answer is correct. So it prints your, okay, here. So if I take the ratio of it, it's all 1, 1, 1, guys here. So if you have to calculate the total 6 weight, the first to be selected, any one can be selected. So if suppose the first 8 is selected, so 80 will be the answer. 80 will be the cost with the 8, and then with 2 it will be 20. Okay, 8 cannot be selected because 6 is the total capacity here. So definitely we can select either the 6 or 4 or 2 together, right? So if I select 6, also the answer is 60. If I select 4 and 2 together, also it is 40 plus 20, 60. So the final answer is 60. Let's change the value a little bit here and see, because this was very straightforward. So this I will change it to 50, suppose, and this I will change it to 20, and this I will change it to maybe 40. Okay. So now in this scenario, what would be the answer? And is it correct or not? The answer is 70. It means if you solve this problem, the answer which we'll get is 10 here, 10 here, right? 20 by 2. This will be 12. Then 10 and 3, 1.3. Okay, so yeah, this will be 50 and 60, 70. So yes, 70 is the correct answer. You can match this answers, solve it using step-by-step method. What will be the solution for this? And you will end up having 70 as an answer. Okay, so this is how we'll write the code for knapsack problem. Fractional knapsack problem, basically, where this is the logic which I have taken into consideration. You can use any other logic also. And then here you have to keep a check that while the complete 6 kg is selected, meaning 6, we have to reduce every time when we select a weight until unless it is 0, like there is no more space left in the bag. Till then, you have to keep on selecting the elements, and while selecting, you have to convert first into the ratio. And if this conversion the ratio is initialized to 0. So if this conversion is greater than ratio, then you have to select that item, meaning I will be assigned to J. So J here is being selected, right? You can see here in the next line of code. Selected meaning the sum is being calculated for that element. Okay. And the ratio value is updated with this new ratio, because we have to find out the order in decreasing order, right? So greater value is what you have to find out every time. So next value we have to find out which is greater than this. Right? So this is how this will work. And then if at all fractional part has not to be selected, then in that case, the sum will be straight away the value of the profit value of that element. Okay. That is what is considered here. And then final profit will be stored indefinitely in this variable sum after all the iterations. So this is the output. So this is all about the code for fractional knapsack. Now let's talk about Prim's minimal spanning tree. So before talking about Prim's minimal spanning tree, what is a tree? So a tree is that collection of vertices and edges which is not having any cycle in it. Cycle meaning if you start from a given vertex and follow the alternate sequence of vertices and edges, you should not reach back to the same vertex from where it started. That is called as your cycle. So if a cycle doesn't exist in the collection of vertices and edges alternatively arranged, then it is called as your tree. Now what is spanning tree? So spanning tree is that tree which spans all the vertices exactly once. Okay, and as it is a tree, it should not form a cycle. We construct a spanning tree from a given graph. Okay, so if suppose a graph has number of vertices as v, then in the spanning tree also we should have the number of vertices as v. Okay, if suppose the graph has number of edges as e, spanning tree will have less than the total number of edges in the graph. Okay, for a given graph, there can be multiple spanning trees. More than one spanning trees is possible for any given graph. The only constraint that spanning tree holds here is that all the vertices should be connected. Okay, it should be a connected tree, meaning there should not be any vertex which is left out. All the vertices should be connected. That is, there should be at least one edge between any two pair of vertices. Okay, and the edges has to be selected in such a way that it should not form a cycle. Then you will obtain a spanning tree. Let's see an example here for a spanning tree. How to find out spanning tree. Then I'll come to how to find out spanning tree using Prim's algorithm. So suppose this is the example graph here. Now here I have to find out the spanning tree. So the first thing said was that all the vertices should be covered. So let me draw all the vertices. Okay, A, B, C, D, E, and F. I'll draw one more here to tell you that there can be multiple spanning trees for a given graph. E, and this is your F. Okay, so first let's consider this part. In this, if I select, suppose I start from vertex A and I select between A to B, I select this particular edge. Okay, between A to C, suppose I select this. I cannot select C to B because it will form a cycle. Then next, between these two, there is no edge. Between F and E, if I select, suppose this edge, having 9 as a weight. Between C to E, there is an edge. So suppose I selected this. Between E and D, there is one edge. Let's select this. This is one spanning tree where you can see all the vertices are covered and number of edges will always be one less than the number of vertices, as you can see in this example for a spanning tree. So number of vertices is same as that total number of vertices. Number of edges will be always one less than the total number of vertices. You can see 1, 2, 3, 4, 5, 6 vertices are there. And how many edges are there? 1, 2, 3, 4, 5. So this formula holds true. Now coming to the another example of spanning tree. Can there be one more spanning tree? Yes, if you select different edges, different spanning trees you will obtain. So suppose between A and F I select this edge 5. Between E and F I select this edge 9. Between A and C I select this edge 6. Between C and B I select this edge 3. Between C and D I select this edge 7. So all the vertices are covered here and number of edges are one less than the vertices, right? So this is also another spanning tree. Similarly, you can have one more spanning tree. Let's see that as well. So A, B, C, D, F, and E. This time I select between A and B, suppose this. Between C and B, if I select 3. Between E and D, if I select 2. Between F, E and F, I select 9. Between C and A, no, I can't select. Between C and E, can we select? Yes, 1. So yes, this is another spanning tree. So you can see all the spanning trees are different in look, right? But this constraint, that number of vertices is same as the total number of vertices and total number of edges is one less than the total number of vertices in the tree, in the spanning tree. Always holds true. Okay. So this is how we construct a spanning tree. Now what is minimal spanning tree? So the spanning tree, which is having the least total sum of weights of the edges, which has the minimal total sum of the weight of edges, is your minimal spanning tree. Okay. To find out a minimal spanning tree, there are two algorithms, two approaches. One is your Prim's minimal spanning tree, another is Kruskal's minimal spanning tree. So these are the name of the two scientists who gave this approach, and the name of these two algorithms is behind their name itself. That is Prim's and Kruskal's. Okay, now let's see with the help of this example how we can find a minimal spanning tree. Okay, so here I'll be using Prim's approach to find out the minimal spanning tree. Then we'll understand the Kruskal's approach also to find out the minimal spanning tree. So using Prim's approach to find out minimal spanning tree, what is done in Prim's approach is that it will start from one of the source vertex. Okay, suppose this is the source vertex. So from here, we will see how many edges are there. 4, 6, and 5. I'm talking about the weights. So B, C, and F, 3 vertices are being covered. In these 3 edges, which is the minimum? This is the minimum. So this will be selected. As we are finding the overall minimum weight, so we'll always consider the minimum one. To go now, we have reached to B. To go from B to any other, there is only one path, right? To go from B to C, that is having 3 as a weight. So we'll go here, 3 as a weight. Now to go from C, there are 3 edges, 6, 1, and 7. Among these 3, which is the minimum? To go to E is the minimum, that is 1. So we will select that. Okay. Now we reach to E. To go from E, which was the minimum? which is the minimum in these two. Either 2 or 9 can be taken. So in these two, the minimum path is 2. So we'll go from E to D with the weight 2. Is all the vertices covered? No. F is still remaining. So to consider F, which is the minimum path from E, which we have 9, and from A we have 5. So we'll consider from A to go to this, that is 5. So in this Prim's algorithm, what we are doing is that after reaching to every vertex, we are finding out which is the minimum weight to go further ahead. And to every step, we are finding the minimum weight, and finally we reach to a conclusion of the overall minimum weight, overall total minimum weight, right? So this is your minimal spanning tree using Prim's algorithm. Now, talking about Kruskal's minimal spanning tree, the approach of solving minimal spanning tree with the help of Kruskal's algorithm. So the difference in approach here is that it will consider the minimum weight in the complete cluster of edges. So among all the edges present here, which is the minimum edge? This is the minimum edge, right? So this will be considered, which is between C and E. So between C and E, there is one as a weight, there's an edge. Now after this, which is the minimum weight? This one. So between E and D, it will be considered. Just checking that there should not be any cycle at any given point of time in the tree, right? Next, which is the minimum? 3 is the minimum. So this path has to be selected. So between C and B, 3 is selected. Now, which is the next minimum? 4 is the minimum. So between A and B, the next path to be selected is 4. After 4, which is the minimum? 5 is the minimum weight. So between A and F, this 5 will be selected. And this is hence the minimal spanning tree. So you can see the minimal spanning tree obtained in this using Prim's approach and using Kruskal's approach, both is same, because both is helping us find the minimal spanning tree, but the approach is different. In Prim's algorithm, locally, starting from one vertex, any one vertex, which can be considered as source vertex, we were finding the minimum weights of the edges. And whichever is the minimum weight, using that, go to the next vertex. Then at that vertex, find the minimum weight, right? This was the approach. But in Kruskal's algorithm, the approach is that find out the overall minimum weight, then the next minimum and so on. Okay, so these are the two approaches to find the minimal spanning tree. Now let's see the code for Prim's minimal spanning tree in Java. So now let's go to the IDE and see how the code actually looks like for this Prim's minimal spanning tree in Java. So here already I have created this file here. Okay, I'll just quickly run through it. So in the main method, you can see I have just created an object for this class in which all the code is written. And then this is the input to the program. Okay. And here just the Prim's minimal spanning tree is called, okay, on the given graph. The input I have already written the same which I considered right now to construct the adjacency matrix. So this adjacency matrix becomes the input to the program. Okay. So the program logic is basically into this. That is, you have to find out. Okay. So this is here. So there is two things. One is that you have to keep track of which all vertices have been visited, because you don't have to revisit any of the vertices, right? And second, what is the value of the edge which is considered when we visited that vertex? Okay, so these two things has to be considered. So suppose I am considering the first row, meaning the first vertex, correct? If I am considering first row, meaning the vertex is A, which I am considering. So eighth vertex, which is the minimum among all these. Okay. So to represent zeros, that is the minimum values actually here, we will use some higher or maximum value. You can use like 999 or 9999 or a maximum value. So max value is a constant already defined in Java, which can be also used to represent these values. So we should not represent these values with zeros, but with some maximum value, because we have to select the minimum value here among this particular row. Whichever is the minimum value. So among 4, 6 and 5, the minimum value is 4. So that will be picked. And next vertex to be visited will be now B. That is the column number for this. Okay, so if I represent the rows, if j represents the columns, and if minimum element in this is found to be 1, so j value will be 1 now. That is this second column. Okay, so this is the logic here. So that's what is done over here. That is for 0 to all the vertices, the key value is selected, which is set as the maximum value. Okay, and initially uh, in the minimum spanning tree set, whichever vertices are selected, all these are selected to be false. Initially, all the visited vertices will be set as false. Once we visit any particular vertex, it will be changed to true. Okay, so that we'll keep track of that which all vertices are visited and which are not. So in the second part of the code, this is what is done. So for all the vertices, we'll find out the minimum. Okay, and here the condition check is done that it should not be equal to 0 also. So you can keep 0 as well. Okay, but just make sure that it is minimum, but it is not 0. Okay, so this is what the check is here. If the graph value is not equal to 0 and this is false, meaning it is not a visited node or visited vertex, and also the value of it is less than the key value, and key is every time the previously selected vertex value, right? Meaning what is the value of the weight of the edge which we took to reach to that vertex V is actually the key. Okay, which was initially set to be here as the maximum values. If it is less, then that becomes your next parent node, or that becomes your next visited node, and the key value becomes the next edge which is traversed to reach to that particular vertex. Okay, so this is the main code here. And then finally, just to print the values, we have used one for loop here. So this is all about the complete code of minimal spanning tree using Prim's algorithm or Prim's approach. And so let's run this code and check if we are getting the same output, that is 1, 2, 3, 4, 5 or not. So yes, the code is executed. You can see 4, 3, 2, 1 is selected as the output. Let's see if it verifies if it is correct output or not. So going to the code again. So here 1, 2, 3, 4, 5 should be the output, right? So 5 is not considered. Let's see why. This was set to be 5 vertices in total. That's why. So now what number of vertices is 6 actually. So it should go till 6, right? So let's see that and execute it again. So now you can see 4, 3, 2, 1 and 5 is being considered in the final Prim's minimal spanning tree. The weights which are considered finally are these. So I hope the output is correct as per our input. So this is all about the implementation of Prim's minimal spanning tree in Java. Let us see the time complexity of Prim's algorithm. So here the time complexity of Prim's algorithm is V square when we use adjacency matrix approach to implement it. Otherwise, if you use min heap, then the time complexity is V plus E log V, where V is the number of vertices and E is the number of edges. And if you use Fibonacci heap, then the time complexity for Prim's algorithm becomes O of E log V. Okay, so this is your worst case time complexities actually. Now, adjacency matrix approach is what we use to implement Prim's algorithm in this session, right? Here, why it was V square? Because if you remember, we used 2 for loops to implement. One for loop was to traverse each and every vertex, right? Then second for loop was to traverse all the edges connecting between the visited vertex and unvisited vertex, right? So because of these two for loops which run from 1 to n, that is 1 to v, where v is the number of vertices, the total time complexity of Prim's algorithm was v square, and all other part of the algorithm or all other part of the code took only constant time to execute, so that was ignored. And finally, these two for loops play an important role in figuring out the total time complexity of Prim's algorithm, which was v square. Similarly, Prim's algorithm can be implemented using min heap as well as Fibonacci heap. In that case, these are the time complexities for it. So this was all about your Prim's algorithm time complexity.
How quicksort works, okay, and how it follows the paradigm of divide and conquer. Okay, so again, it is a sorting algorithm. That means you have an array and you're trying to sort this array. That's it. Okay, now one of the most commonly used algorithm is this quicksort algorithm. Why? Because it follows a divide and conquer paradigm, which is efficient as compared to our traditional sorting algorithms, right? Like bubble sort, selection sort, or insertion sort. So this is the time complexity. Okay, so now what about the rest of the things? Recursion is used in this quicksort algorithm. You are using recursion. Now, unless and until we hit the base case, we are going to divide our sub problems, and we are going to divide our problem into sub problems and sub problems, and then we combine them. Okay, at the end we will have the sorted array, so that is a combined part. Okay, so how does this quicksort works? It works in such a manner that you pick up an element and you make this element as pivot, and based on this element, this is your pivot element. Let's suppose this can be any element, but for simplicity I'm taking this as the last element in the array. It can be first, but its time complexity depends on which element you are picking. Okay, so now we are picking up this element that is there. This is the last element, and this is our pivot. Now, based on this pivot element, we will try to divide our array in such a way that on the left hand side, all the elements, this is our pivot, this will have its original position after one iteration. Let's suppose this is 3, then this 3 will be here, and this will be the original position of this 3 when we sort our array. Now listen to me carefully, this is very important. Now this is our pivot, this is 3, and this will be placed after one iteration. This will be placed here in such a way that all the elements on the left hand side of this pivot will be less than, and all the elements that will be present on the right hand side will be greater than. And this will be, when we sort this array at index 2, you will have this element in the sorted array as well. Okay, is this thing clear? So now let's see the quicksort. Okay, therein we have two algorithms, or you can say it is divided into two sections. One is the quicksort algorithm, for that the quicksort, and the other is partition. Okay, so this is our quicksort, and what we do, we always, just like in binary search, always whenever beginning is less than end, we try to divide it further. Okay, then we try to partition it. Now once we partition it, the partition function will be called, and we are passing in the arguments as array and the beginning index and the ending index. Now let's see first this partition algorithm, how it is partitioning it, and then we'll try to see these two portions, because then what we do, we have the left side and then we have the right side. But first, this is our left, this is our right. Let's try to partition it first. Okay, how partition is done. So if you talk about partition algorithm, we set the index, that is the last index, as pivot, right? And we have something that is known as the p index, which is currently at beginning -1, which is at somewhere right here. Okay, now how would you, now our main objective of this partition is that this element that is there, which is pivot, should have, after this partition is done, this element should be at its original position. That is the main focus of this partition algorithm, is that after the entire this partition is done, this element should be at its original position. So now once this thing is done, after that, what we do, we execute this for loop and we start from beginning to end -1. Okay, we have this beginning and which is end -1, except this element, and then what we do, we check if ARR of I is less than pivot. Okay, if it is, then we swap it, okay, with the next location. Okay, now we check if this is the ARR of I, which is this index, this I is over here. Now if this I is less than the pivot, let's talk about this I first. So let's suppose there is an element which is 2. Now you have 0, 1, 2, 3 as the indexes, and these are the elements 5, 10, 9, 6 and 7. Okay, now let's try to understand how the partition works. So obviously here beginning 0 is less than 4, then we call the partition and we return the pivot index. Okay, so now here this is the pivot at start, I told you guys, right? Now what happens, we will divide our array in such a way that this 7 is here, right? After first iteration, this 7 will be at its original position, that is this. Okay, this 7, and rest of the elements you see 5 and 10, you see, are replaced. If you have this 7 over here, These are the elements which are less than 7, and these are the elements which are greater than 7. You see the divide approach that is happening over here. 7 is over here, and what is happening? This 5 is less than 7, this 6 is less than 7, and you have this 10 which is greater than 7, and 9 which is greater than 7. Now let's go back to this algorithm. Now what is happening? We have this index which is at beginning 0, 1, 2, 3, 4, 5, 6, and 7. This is 7 index, this is our pivot. Okay, we loop around from beginning to end -1. This is our beginning. Okay, and this is our I iterator, and we have something that is p index which is at this location which is currently -1. Okay, now what we are doing, we have this end over here, right? We have this end pointer over here. That means we are looping from this here to here, not the last element. Now we check if ARR of I, if this element is less than pivot. This is our pivot. If this is less than, if this is less than, then what we do, we swap ARR of I, that is this element, with p index. Now what is happening? P index is currently at -1. So we need to change this from here to here. We first increment our p index. We do the p index over here. That means we are currently at this location. We swap this element with itself. Now, why we are doing this? It will make sense. You might be thinking this is a redundant step. No, that is the reason I made explicitly. I am mentioning it here so that you can see the difference. Why we are swapping this number with itself. Okay. So now once we are done with this step, the next step is we are still in this for loop, right? We check the next element. Now let's suppose this element is not less than this element. Let's suppose this was 5 and this was 3. Okay, this element was 3 and this element was 10. Okay, now this element is not less than pivot. Okay, so what we do, we increment our I. So I is here and p index is still here because we just incremented it, right? So this is 10. Now this is, let's suppose this is 2. Okay, this is 2, which is less than pivot. Now what happens? Now we are having the p index over here. What we do, we increment our p index to this position because this is less than 2 is less than 5. Then what we do, we swap these positions. This is I and this is p index. So this is what is happening, swapping ARR of I, that is this, and ARR of p index. We swapped them. So now we have 2 over here and 10 over here. And similarly, what we have 3 over here. Now p index is at this position. Now let's suppose somehow all the rest of the elements, right? This was 3, this was 10 earlier, this was 2. And rest of the elements are 11, 12, 13 and 14. Okay, all the elements are greater than. Now, once this entire loop is done, okay, we have p index at this position and I would have been over here. Okay. Now, if I would have been over here, then what we are doing at the end, we are swapping these two indexes at the end. So we are swapping this index, that is this 10, and the last index with this, that means 5 is over here and this 10 will be over here and rest of the elements are as it is. This is a very tricky algorithm in terms of how you maintain these things. So you need to reiterate through this again and again in order to understand this. Okay. So you need to understand what is happening. So let me just go here and show you guys again in the demonstration what happened. So now what happened? So this is less than pivot, right? It got swapped with itself. This 10 is greater than pivot. It remained over here. This 9 is greater than pivot. It remained over here for now. This 6 is less than pivot. What happened? These two elements got swapped. You see 6 and 10 got swapped. 6 is over here and 10 is over here. Now, once this entire iteration is done, then what we did, we swapped this with this index because p index was here, p index plus 1, that means this index, we swapped these two elements, that is 9 and 7. So 7 is over here, 9 is over here. So this is what happened after first step. If you sort this array, this 7 would be exactly at this position in the sorted array as well. Okay, is this thing clear? I know this is getting complicated, this partition thing. Now you have partitioned it. Now what you're doing, you are returning this index. Okay, you see at the end, you are returning this p index plus 1. That means you are returning this index, this particular index. So you're returning this index, that is 2. Now again, if you observe carefully, now we have in the next step a left portion wherein we call this partition again and the right portion wherein we call this partition again. Okay, so we have beginning, same thing, beginning and pivot. Pivot will be the last element. Beginning and pivot will be the last element. So again, we sort them in such a manner unless and until beginning is less than end. If beginning is not less than end, we will stop, which will be the case in these two cases. Okay. Now, after this entire step is done, we will have this sorted array, and these two will be done in just 2 steps. Okay. Just 2 steps, your entire array will be sorted. Is this thing clear, guys? I know you need to reiterate through the algorithm again and again. You see, this is the implementation of quick sort. You see, it's quick sort is over here. You have the array, you have the p index, you have the r, that is the beginning index and the ending index. This is your beginning and this is your end. Okay, p and r. So you are checking if p is less than r, that is beginning is less than end. Okay, then you partition. Your partition is called. You return one index and then you call again this quick sort. Same thing again, but this time around you call it from 0, that is your beginning, and pivot index -1, because pivot index is originally at its own position, it won't change. So you will have this index that is there, and you call the quick sort again on this portion. And in this, what you do, pivot index +1, that is q +1. Here you have this q -1. Okay, so you have this partition, that is p index. Okay, so q -1, that means you're talking about q +1 in this portion. You're talking about this element q +1, and the r, that is your end, and you call the quick sort again on this portion. Okay, this is a little bit you might get confused or you might get stuck. This is that kind of an algorithm, and this is very important algorithm to understand divide and conquer strategy, how it is doing this divide and conquer. Okay, so you see, he divided it, find out the pivot and pivot it at its original position, divide and conquer, done. Again, divide, conquer and combine, divide, conquer and combine. At the end, the combine step will take place, which will be your sorted array. 1 2 3 4 5. Okay, so if you see, this is the implementation of quick sort. But what about the partition? Partition is much more simpler. You see, partition, then you have this last element as the pivot. You pick the pivot index, which is a pointer which helps you to change or swap the indexes, right? So you have pivot index over here, then you loop around it, and then finally the last swap. That's it, done. Okay, and then you finally return the pivot index. So in this loop, what you do, you just swap around and in such a way that all the elements from this pivot index will be less than, on all the elements that are on the right hand side will be greater than. What is merge sort? If we talk about merge sort, let's try to understand first sorting. So sorting is a mechanism of giving order to your values, right? So let's suppose you have some values, random values, 10, 30, and then you have 5, 2, 1, and so on, right? You have these values, and now you want to maintain some order. So in order to visualize this data, let's suppose you want to see the ascending order of it or the descending order of it. That is what you mean by sorting. So let's suppose you have a class, and in that class you have several roll numbers, and some of the roll numbers are not present, and then you want to sort those roll numbers in terms of ascending or descending order. That is when you require sorting. So this is the basic intuition behind sorting, trying to give order to some kind of values or some kind of a data set, right? So in this particular tutorial, we are going to talk about merge sort. So merge sort is a classical sorting algorithm. In this sorting, every time your problem is divided into sub problems so that your problem set is reduced, and then you will be focusing on that sub problem. Similarly, every time when you're dividing your sub problems, you will keep on dividing it unless and until there is only one element left, right? If you compare it with simpler sorting algorithms like bubble is there, insertion is there, selection is there, quick is there, when you talk about its time complexity as compared to these algorithms, this is very much efficient. Now, it follows a paradigm of divide and conquer. What does this mean? This means that first you keep on dividing your sub problems, and then you will conquer those problems, and then you will combine those things. Okay. So herein we will see when you are trying to divide your sub problems, and then when you have your problem set and those problem sets are conquered, that means those problems are further, when you talk about in this example, those sub problems are sorted in this case. And then you have conquered them, and then you will combine them. That is your merge phase, wherein you will be combining your problem again, and then forming again a single sub problem. So every time you will be dividing that sub problem, you will be conquering it and combining it. So this is how this divide and conquer paradigm works. So basically, when you're dealing with merge sort, you are focusing on two functions, that is your merge function and your merge sort function. So now let's talk about this divide. That means you're dividing your subproblems, which continues unless and until there is only one element left, because one element in itself is sorted, right? Now this is your divide phase. What about conquer? Basically, you are conquering those individual sets and then merging those two subproblems into a single problem. And finally, you will be doing it on each step. And finally, you have your original array, which is sorted. Now let's talk about merge sort algorithm. So first, let's talk about merge sort method. So in this method, what we are doing, we are dividing our array into further sub arrays. How we are going to do that? We are basically, if we have this array, right? And this array, let's suppose this contains 8 elements, right? This is our array. And let's suppose this is our left pointer and this is our right pointer. And now what we are doing, we are dividing it. So we need some kind of iterator wherein we will store the sum of, and we try to calculate the mid value. How would you do it? In simple words, we calculate left plus right divided by 2. That's it, right? So we have this division, and then we will divide this part because we are calling this function again, right, on the left hand side. So this is going to call on this side. That is, we will be talking about now only 3 elements. So this is, let's suppose, or let's take 4 elements on this side and 4 elements on this side. So our mid will be 3.5. So we'll be talking about elements from 0 to 3. So we will be talking about 4 elements, and then further these 2 steps are remain. Why? Because we are implementing this in recursive fashion. So now let's suppose this is our first function call, and you have these 3 steps. Let's name it 1, 2, and 3. Okay. So in the first function call, 1, 2, and 3. So this is the first function call, and in this we're calling again. This is the second function call, and we are calling again these 2 remaining, right? And we are calling again 1, 2, and 3, right? So in this case, again, we are calling it on these 4 elements, and it will be divided into further 2 elements, 0 and 1, right? And in this case, again, this will be called on these 2 elements, right? Here we are talking about only 2 elements. So this is the third function call, and again, we will be dividing it. These 2 and 3 steps are still remaining. So in the fourth step, what we are dealing with only single element, right? And in this case, we are talking about only this element, right? And further, we will not be able to divide it. And in that case, our left will be greater than or equal to right. And in this case, it will be equal to. So we will return. So now it will be returned, right? And then whatever was the left over, right? Now we talk about this single element, the other element that was left behind. We'll talk about that. So again, that will be divided into 1, right? And again, this second option, I'll just erase it because it looks a little bit messy. So now what happens? Let me just put it again in red. So here we called this 4th time, and this time it returned, right? So in this case, now we will be on the second step. Now again, it will be called on that single element. And again, left will be greater than or equal to. In this case, it will be equal to, and then we return. So again, we are returning. So we have these 2 elements, 1 and 1. That means not 1 and 1 element, but there is only a single element in both these arrays, right? Why I'm saying that in these 2 arrays, we will check when we talk about merge. Okay, we'll see how that is implemented. Okay, so now these 2 function calls are done, and then we deal with merge. So you have these elements, and here you have how many elements? You have 5 elements, right? And now you're dividing it into 3 and 2. Now this is your first step. The second step will be this. So now will you go ahead and create this as your third step? That means you will move on to this? No, because we saw unless and until there is no left, right? We will not go to the right. So this is your second step. Then this will be your third step. This will be your fourth step. Now you will move on to your fifth step, right? And now once you don't have anything on the left, nothing on the right, then what happens? Will this be your sixth step? No, your sixth step will be merge. So let's move on to merge now. So in the merge function, if you see, the algorithm for that is simple, that you create two sub arrays, that is, one is your left array and another is your right sub array. Now in this, you have obviously in the last case, if you have seen, we have a single element here and a single element here. Now once we have deduced out the length of these arrays, what should be the length of these sub arrays, and we have declared the length or declared these arrays, and then we have initialized these arrays. Once these three steps are done, then what we are going to do, we are going to create three iterators, I, J and K, and those iterators deal with, I iterator will deal with the left array, J iterator deal with right array, and K with the original array, which helps us to insert the elements. So once we have everything in place, what we are going to do, the next step is comparing the values, right? If this element, that is the element in left array, is less than the element in the right array, we are going to insert that in the original array. So now let's suppose you have 10 here and 23 here. So 10 is less than, so we are going to insert this and we increment the K pointer. And now also our I pointer will be incremented. It was earlier, it was 0 and it will go to 1, right? And now what happens? Now our I is pointing to 1 and our length is also 1. So now that in that case, when one of the array is exhausted, the next array, whichever is left, right? It can be either the left array or the right array. Those elements will be directly inserted in the original array, because we know for the fact that both of these left as well as right arrays will be sorted in itself. Okay. So here we had our steps, right? And this will be the sixth step wherein we are going to merge this thing. Now, will this be your seventh step? No, your seventh step will not be this. Your seventh step will be here. This will be your seventh step. Now, sixth step is done. Now you will be dividing it and you will be creating all those arrays. Now, once you have your right array, and there is no right because this left is already done. And now you had your right left. Now this is also done. Now your eighth step will be this, that you will be merging it. This will be your eighth step. Then you will be merging it. Now, will this be your ninth step? No. You have your this array, that is your left array in place. But what about the right array? Is this in place? No, it is not. So now let's try to calculate that. Now, what will be your ninth step? This left is done. This is your ninth step. Then what will be your 10th step? This is your 10th step. Well, now there is no left, right? Now we'll move on to this right. So this is your 11th step, because this is the right side of it, right? And now when you don't have anything on the right, now you will be merging these two steps, and this will be your 12th step, which is over here. So this is your 12th step. That means you will be merging these two, and the final sorted array is this array, and you will get this array in the 12th step. So you see 10, 11, 16, 20 and 13. Now, if you observe carefully, you have these individual arrays, 1 and 1. So now, while you are merging them, you are also sorting them. So the left array is sorted. And same thing happens on the right hand side as well. If you see 3 and 4, these two elements are sorted in this left array. So this is the reason in the right array, right? Not the left array. So now, when you are merging them, you will get again an array which is sorted in itself. You see 10, 16 and 23. So if one of the array is exhausted, the next array elements can be directly inserted in your original array. Let me erase this. And you see, you have your left array, which is sorted, and then you are merging it with the right array, which is also sorted. Now, if one of the arrays is exhausted, the next array, either it can be left array or the right array, the elements from that array can be directly inserted in the original array, because we know the elements itself in either of the arrays, either the left or the right, are sorted. Okay. So this is how you execute your merge function. Now let's look at merge sort implementation. Now we know that we need to implement two methods, right? First is the merge sort method and the second is the merge method. So first let's look how to implement this merge sort. So basically this method will take three arguments: the array, the starting point and the ending point. That is your starting index, that is 0. And if you have an array in which you have 8 elements, that means you have 7 indexes, right? So this will be 7. Okay. Now we will only run this sorting merge sort function when our start is less than what? Right, or the end. That is, start is less than right. Because we know only then we will be dividing it into further segments. That is, first it will be 8 elements, then we'll be dealing with only 4, then we'll be dealing with only 2 elements. That this means this you have 4 here, you were having 8 here, then we'll be dealing with 2, then finally we'll be dealing with 1 elements, and that's it, right? So this function will be called again and again and again unless and until you have your left less than your right, okay, or start is less than right. Now when you have this single one elements each, the segment, and these are sorted, then you will be calling your merge function on this and you will be sorting them in a single array. In this case it was, I guess, 10 and 23. Now it will be sorted to 10 and 23, right? So this is the how you implement your merge sort. Obviously we know that how recursion will occur, right? So let me just put the actuation record, how it looks. It will look like something this. Let's take an example here. Let's name these functions as 1, 2 and 3. So when you have your left, if you have your left, it will be called, right? This function will call this actuation record. There will be next actuation record. This will call this function, right? And these two are left behind. So again, this will be called unless and until you have your left. Now let's suppose you don't have any left, right? That means the 1 and 1 case wherein you have only single element left. In that case, it will return back. Now these statements will never be executed because you're returning it. This condition is not true, right? This condition is not true. So nothing will happen. These statements will never be executed, right? So nothing will happen and it will return back, right, to the previous statement where we call this function. So it will go on to the second. Now similarly, the second case is nothing but your right. You will be calling this on your right function. Now if that is the case, you have your right, it will call this again. It will again start the procedure of calling these 1, 2, 3 again. But if it is not the case, it will return back. And finally the merge will happen. So in this case, when we have 1 and 1, that is 10 and 23, the last two elements, then it will be called, and this statement, this step third will be executed. That is, your merge will be executed. Now let's look at how you can merge these two elements. So in the merge function or in the merge method, you will have 4 arguments: the array, the left pointer, the middle index, and the right index. That is your endpoint. So in first case, wherein you have only 1 and 1 elements, that is, you have single elements, that is 10 and 23. In that case, your index, obviously your lengths, you will calculate your lengths with this formula. We can calculate these lengths and it will be 1 and 1, right? And then you initialize, that is, first calculating length is this, what we do here. Then the second step is initializing our arrays or declaring our arrays. Then initializing our arrays, these arrays, that means the array that we just created, 10 and 23. These are new arrays. This is your left array, ARR, and this is your right array. Okay. So you created them, you inserted the values. Here you insert your values. Insertion or initialization. Here you are just declaring it. Okay. You're just declaring it. Done. These are the first 3 steps that you need to do. So calculate length, declare your array, and initialize your array. Done. The next step is that we calculate. Let's suppose you have this case 10 and 23, right? These indexes are 0 and 0. So this is your I and this is your J. And the K pointer is nothing but used for replacing elements in our original array, which is ARR, obviously, right? And this K points to the index that is 0. The rest of the elements is whatever, we don't require them because we are just dealing with these elements and replacing them, okay? So this K pointer points to 0 index. Now in that case, we have I, which is pointing to 0 and length is 1. Obviously, it is less than. Same case will happen in here. 0 is less than L2, right? Now we compare these two values. If the element, first we will insert the lesser elements. That is, 10 is less than 23. Yes, it is. So what we do, we insert this left array, whatever is the content in it, that is 10 in this. And then what we do, we increment our I. So I will be pointing now to first. Now I will be incremented to 1. Now what will happen? This I is incremented. So this block is done. this block won't be executed. Then we have finally k plus plus. Now what happens? We increment our k because we have already inserted it in this, and now k will be pointing to 1. Okay, done. But now when we again go into this while loop, we are still in this while loop, right? Now this I is 1. So I is not less than L1 because both of them are pointing to 1, right? The I is 1 and length is also 1. So, and both these statements need to be true because we are using the AND, logical AND operator, right? So we are out of this for loop. Now what about this element, the remaining element, right? So for that, what we do, we have this and this while loop in place. So this is for the left array that we have if some of the elements are left, right? And we know for the fact that left array and right array will be sorted in itself because that's how we proceed, right? So in this case, the left array is done. But what about the right array elements? That was 23 in our case. So that will be directly inserted. You see that we have directly inserted that in our, this k pointer was pointing to here, and we have directly inserted this 23 in here. And whatever, if we have more elements, let's suppose we have 23 and 53, we know this is sorted. So we'll be directly inserting them in this and incrementing our k pointer and also the j pointer, because this j, we are only executing this because j should be less than L2. We will be comparing it with the length of, with the number of elements, right? If we have 2 elements, we will be going from, we will be traversing 2 times. So in this case, j was here and we had only single element and j was equal to 0 and the length was 1. So obviously j is less than, this means that 0 is less than 1, and we inserted 23. We inserted 23 and we incremented the k pointer. That means k is pointing here now in this location, and we incremented the k pointer and also the j pointer. So j is incremented and j will be 1, and now 1 is not less than 1. So we are out of this loop. And this will not be executed. Why? This was the reason why we were out of this initial while loop, because 1 is not less than 1, right? So this is how you insert rest of the elements that are left behind. And this does not happen only in this case. This will happen in each and every case wherein your left array or your right array have elements which are not compared, that will be directly inserted in your array, original array. Okay. Now let's try to implement this. Whatever we have written, we are going to copy paste the same code in our editor. The editor that I'm going to use is Sublime Text. Now, if you see, we have a class and that is named as merge sort. And in this, we have merge function, which takes arguments array, left and right and the mid. Okay. We calculated the lengths and then we declared the arrays. Then we initialize these arrays with the help of these 2 for loops. Then we have these pointers, which will help us to insert the values, right? And then we inserted the values if we are comparing and both of the arrays, that is the left array and the right array, have elements in them. Once we don't have elements, then we will check if there are any elements in the left array and if there are any elements in the right array. Once we are done with that, we have our array and which is sorted, right? We merge them, those 2 arrays, left array and sub array, we merge them. And this is how you implement your merge sort function. In this, we have 3 arguments, start and right. And obviously start should not be greater than or equal to right. And in that case, we will be returning right. And if you have seen this is how we calculate mid, right? And then we call this on the left part and on the right part, and then we merge them. This is your merge sort, right? And then we have this display function wherein we are just iterating through the array and printing out the elements. You have your main function over here, and in this we are using a static array. Then we created an object, this merge sort ob. This is your object, merge sort of class merge sort. And we have first displayed the original array, that is unsorted array. And then what we did, we called merge sort function with the set of arguments, and then we printed out the array because we are changing in the original array. So we are displaying the array that was there with the sorted elements, right? So now let's save this file and let's try to run this. Open up your command prompt and just type in, obviously you should be in the same drive wherein you have stored it, right? So we write javac and the name of the file, that is merge sort.java. We compiled it, and then what we did, we ran it. The command for that is java merge sort. So you see, you have your original array as 6, 5, 12, 10, 9, 1, and then you sorted it out, and the sorted array is 1, 5, 6, 9, 10, and 12. So this is how you implement merge sort. So we have seen all the functions plus the driver function as well as the display function. Now let's try to analyze merge sort. First, we are going to cover number of comparisons. Then, is it stable or unstable algorithm? Then we are going to cover, is it in place or out place algorithm? So now let's try to understand how many comparisons are required when we are dealing with merge sort. So let's take an example. Let's first talk about worst case and then we'll talk about best case. Space complexity, we always talk about worst case. That is big O notation. It can be n, it can be anything, right? So we always talk about big O notations. So let me clear it out and let's talk about this thing. So for worst case, let's take an example. Let's suppose we have, this is the second last step wherein we try to merge these two and we merge them in a single array, right? This is about merging where comparisons happen and then we merge them in a single array. So let's take the second last step. In that, let's do 1, 2, 3, then 4, then 5, then 6, then 7, then 8. So this is the second last step wherein we have these two partitions and we are trying to merge them in a single array. So let's see how many comparisons are required in this step. Okay. So 1 will be compared with 2. So here you have it, 1 comparison, and we'll merge them into a single array. Now this is gone. Now still 2 and 3 are remaining. So now what we do, we compare 3 and 2. So 2 is smaller and it will go in this array. This is also gone. So 3 and 4, 3 is smaller. Now we move on to 5. So 5 is gone. 5 and 6 will be compared. 5 and 4 first will be compared. We have 4, then 5 and 6, we have 5, then we have 5 and 6 and 7, we go 6, then 7 and 8, we have 7. So after this 8 will go directly in this because we know if one of these arrays, that is your left array and right array, if one of them is exhausted, right, the next element will go directly in the merged array. So this is your sorted array and the number of steps or comparisons required is 1, 2, 3, 4, 5, 6 and 7. That is n minus 1. Okay. Now, if we would have the best case scenario wherein this array is sorted, right? 1, 2, in this manner, 1, 2, 3, 4, and then 5, 6, 7, and 8. In this case, this would have been compared, this would have been compared, this would have been compared, and we have this 1, 2, 3 in this array, and rest of the elements would have been directly inserted, 5, 6, 7, and 8. Okay. Let me just write it somewhere else, as this might not be visible to you guys. So just a minute. So what would have happened? So we have this array at the end. We have 1, 2, 3, and then rest of the elements 5, 6, 7, and 8 would have been inserted directly. So the number of compares would have been n by 2, that is 4, right? Only 4 comparisons. But this is the best case, and we never talk about best case. So now let's try to erase everything. And now let's see. So first we have 7 steps, right? Now this we came, how would we evaluated this? By n minus 1. Now what about these two cases? So we have this, first we talk about this array wherein we have 4 elements on this side, and 4 elements on this side. But how would we have evaluated this array? We would have something like this, 2 comparisons, these 2 sub-arrays. This is the left and the right. And then this would have been merged into this, and there would have been another 2 sub-arrays that would have been merged to this, right? So how many comparisons would require to get this merged array? So now let's look at that. Let me erase everything. Now let's talk about these 2 partitions first, right? So now we merge this into that, getting those 4 elements, right? And getting these 4 elements. So now it seems that we could have compared this and then this, and rest one element would have been directly. So 3 comparisons here, and we have similar case here. So 3 plus 3, 6 comparisons. Now, if we evaluate this and put it in a form in the form of formula, it would have been n by 2 minus 1 into 2. Why this 2? Because same thing happens over here. Okay, so we are just doubling it out. So let me put it for in this case we have n equal to 8, and 8 divided by 2 minus 1 into 2. So this is nothing but 4. 4 minus 1 is 3. 3 into 2 is 6. So 6 comparisons, right? So this is the formula. But what happens when we talk about this? How we evaluate it? How would we have evaluated this case? Now let's talk about that. We erase this thing. So in that case, we would have something like this, right? So we would have this 2, and this would have merged into this. And similarly, this would have happened 4 times, right? 3 more times, that is 4 times we would have such scenario. So here the comparisons would have been only one comparison, right? So in that case, it would have been something like 2, n divided by 2 raised power, let me put an arbitrary value like, or let me put a value for in this case, then we will evaluate a formula. So minus 1 divided by 2 raised power 2 into 2 raised power 2, right? So in this case, how many comparisons? We would have n equal to 8, and this is 2 raised power 2, which is 4, which would have resulted in 2. 2 minus 1 is nothing but 1, and multiplied by 4. So 4 comparisons. Make sense? This is one comparison, and this would have directly inserted in. We would have directly inserted in this merged array. So only one comparison is required. Similarly, we have other 3 situations. That is total number of situations. Such situations are 4. So in the first iteration, when we talk about these 8 elements, when n is 8, we had 7 comparisons. Then we had 6 comparisons, and then we had 4 comparisons. So total of 17 comparisons. So now let's try to evaluate a formula so that we will get this 17 as it is for the number of comparisons. So if we talk about this thing, we would have something like this. N, if we evaluate the formula, we have n divided by 2 raised power I minus 1, then minus 1, and then into 2 raised power I minus 1. Now what is this I? This is nothing but your number of levels, okay? And this level is nothing how many times you are going to get that comparison situation. In this case, when n was what? N was 8, we had 3 levels, right? So it would have been something log n to the base 2. Now this would have been only 3, but the last merge is also there, so plus 1, okay? And this is only for the case when n is even. What about odd cases? So we take the seal of this. That is, we take the larger side. So this is the number of levels, that these I. What about this? This is nothing but your comparisons. Your comparisons, how many comparisons you are taking. And this is nothing but your nodes. So if we try to evaluate this thing, this turns out to be what? N, the seal value of log 2 to the base n minus 2 raised power log n to the base 2 plus 1. Now we need to find out that if this 17, if this equation holds, right? So in this case, n was 8, right? And the seal value of log 2 to the base 8 is nothing but 3, right? 2 to the base log 2 to the base 8 plus 1. So now if you evaluate this, this will be 8 into 3 minus 2 raised power 3 plus 1. So this turns out to be 17. So our equation holds, and the formula for calculating number of comparisons is nothing but n. Then you have your seal value of log n to the base 2, right? This is a seal value because we are taking into consideration both even and as well as odd cases. Then minus 2 raised power log n to the base 2 plus 1. What about unstable or stable? Merge sort is a stable algorithm. What does that mean? It means if you have an array wherein you have 1, then you have 3, then you have 2, then you have 4, then you have 2 dash. Now these 2, this 2 and this 2 is repeated, right? Now in the sorted array, this order will be maintained. That is what is known as stability. So you have in your sorted array 1, 2, and then you have 2 dash. That means this 2 and this 2, their order will be maintained in the sorted array as well. So it is stable. And what about in place or out of place? So in place means that you are not using any extra memory, but in our merge sort, as we had already seen, that we were using two arrays, that is the left array and the right array, for storing, which also helps us in comparing the values and then inserting them in the original array. So we are creating extra memory, right? So in that case, this is an out place algorithm. All right. So this is the whole analysis of merge sort. Now let's talk about time and space complexity of merge sort. So first we are going to talk about time complexity. So as you can see that every time we are dividing our problem, or if you have 8 elements, we are dividing our array into further sub-problems. That is, we are dividing it, right? So if we are talking about 8 elements in the first array, then we are talking about 4 elements, then we are dividing into 2 elements, then we are dividing into single element. So every time our problem is reduced by half. So when this is the case wherein you have n, then you will talk about n by 2 elements, then you will talk about n by 4 elements, then you will talk about n by 8 elements, and so on, right? If this is the case, this is the case where you are dealing with log to the base 2 and n. Why this is the case? Let me take an example. So let's suppose your n is 8 in this case, right? Log to the base 2 and value of n is 8. So this is 3. That means you will be dividing your problem 3 times. That is the correct scenario that follows in here. So you have 8 elements, then you are dividing it into 4. Then you are dividing into 2. Then you are dividing into 1. That's it, right? So you have three such instances in this example that you are dividing your problem 3 times into half. So this is the case where your complexity is log n. So to the base 2, obviously. Right? So this is the scenario, but this is a scenario only for the first phase when you are dividing it. But then you are also merging it. That is the second phase. In that phase, you are doing it for all the n operations or all the n elements or iterations. And in that case, you are dealing with all the n elements. So the total time complexity is n into log n. So this is the time complexity of a worst case. And obviously this will be the time complexity for best case, because in best case, only the comparisons, as we already seen, only the comparisons will reduce and rest will remain same, because you're again checking for all the n elements, right? So in that case also, your time complexity will be n log n. And for all the time complexities, that is best case, worst case, and average case, the time complexity of merge sort will be n into log n. Log n because of the reason we are dividing it, and then we are dividing it again and again and again. So this is a case where log to the base 2 comes into picture, and we are doing it for all the n elements. That is in the second phase where we are merging it. So that is your n. So the total time complexity is n into log n. Now, what about the space complexity? If you talk about space complexity, here we are using an extra memory, right? And every time we are using, let's suppose in the last case, we are using memory of size 1. And in the above case, before that, we are using memory of size 2, then 4, then 8. So in the worst case, when we are talking about space required, is that we are using n amount of memory, right? So all the n elements are stored, because in the last step, we are using an auxiliary memory wherein we are storing all the 8 elements. So in that case, what we are doing, we are copying our elements in an auxiliary memory, wherein at worst case, the space that we require is n, that is the number of elements. In this case, we require 8 memory spaces, right? And so the space complexity of merge sort is big O of n, because we are using extra memory, that left and right arrays that we created. And in the worst case, we will be requiring to store elements, which is equal to the number of elements. Now let's try to compare quick sort with merge sort. So we know that in merge sort, every time we are reducing our problem into half, right? So we have first 4 elements, then we have 2, then we have 1, then we merge them. So every time we are splitting our array. That will not be the case in quick sort. In quick sort, we have one pivot element wherein that element is the element wherein the right if we talk about the elements on the right side of the pivot and on the left side of the pivot will be elements either smaller or either greater than. So we have that pivot element as the separator between the elements that are greater than and the elements that are less than. And the pivot will have its original position in the array every time, right? That is how quicksort operates. Now, if we talk about worst case scenario, we have already studied that in worst case time complexity, the time required by merge sort is n log n, which is not the case in quicksort. It will be n square. Now, merge obviously takes n amount of, or if you talk about big O notation, it takes order n space complexity. If you talk about consistency in terms of the size of the elements, it does not depend on whether your data sets are large or small. That means number of items. Wherein it will, if you talk about quicksort, it is faster than other sorting algorithms for small data sets like selection sort. In selection sort, if the data set is small, it will take a huge amount of time. Not huge, but comparatively, quicksort will be faster than selection sort in that case. If we talk about using extra memory or using the array that is there and inserting values in that same array, that is not the case in merge sort. We are using extra memory. This is an outplace algorithm, and in this case it is an in-place algorithm because we are not using any extra space. If we talk about stability, quick merge sort is much more stable in terms of if we have 2 and 2, this 2 will always be in front of this 2. That is what is stability. That means if you have some order at the time of insertion, that order will be maintained, which is not the case in quicksort. So this is the comparison between quick and merge sort. Now let's try to see one of the examples, which is one of the most commonly asked question on merge sort. So you have been given these two sorted arrays, right? And you have to merge them in a single sorted array. So if you see the input that is given to you, this is your one array. Let's name it ARR1 and this is your ARR2. So if you see, this is 1, 5, 8, 10, 20. That is, it is sorted. And similarly, 4, 6, 9, 15. This is also sorted. Now you have to merge them together and the resulting array should also be sorted. So this is your problem. So how can you solve this? So what we are going to do, we are going to create a class and name it merge. And in this, we have one method which takes in arguments, that is your first array, ARR1, ARR2, and then the size of these arrays, that is n and m, which is nothing but size of ARR1 and size of ARR2 respectively. And now we will be creating another array that is A and S, that is your answer array, and we have its size as n plus m. And we will be having our 3 iterators which will help us to insert value in this A and S answer array, right? So what we are going to do, we have this while loop which will iterate. We know I is from 0, I is 0, and it should be less than n, that is the size of this ARR1. And also we have this j pointer which is equal to 0 and it should be less than m, which is size of this ARR2, right? So these are the sizes, okay? So now whenever we are comparing, now we have these two arrays in place. Let's suppose you have 1, 5 and 6 and you have here 4, 5, 3, obviously it is sorted, 5, 8 and 9, right? Now we will be comparing these two elements, and if now we will be comparing these two elements 1 and 5. So 1 is less than 5. So we will be inserting it in the answer array, and we have our k pointer which is pointing to 0th index, and we will be inserting this 1 over here and incrementing this k to here, right? And similarly, we'll be traversing. So we talk right now, our I is less. So we'll increment our pointer and it will be pointing to this location now, or this element in this case, which is 5. So now if you have same situation, right? That means I and j are same. In that case, else part will be executed and we'll be pointing up, our pointer will point to the next location in this array, that is your array 2. So j will be pointing here and we'll be pointing now to 8 and 5 will be inserted. Now what happens after that, we'll be pointing here, that because we are talking about this array, right? As soon as when we have an array which is having 3 elements, let's suppose this is having 3 elements, and we have exhausted it, and in this we have, let's suppose we have 10 elements. Now we only exhausted 3 or 2 in this array. So rest of the array elements, either it can be the left array, that is ARR1, or the right array, that is ARR2. If either of these are having elements which are not traversed, so we know for the fact that both of these array are sorted, so we will be inserting values directly in the answer array with the help of these two while loops. So this while loop is for left side, or ARR1, and this is for right side, that is ARR2. Okay, so we'll be directly inserting the elements in this array, and after that we will be returning this array. So if you see, the return type of this merge is an array, so we'll be returning this array. So this is your merge function. Now what about the other functions? We have display function over here, which is used to display elements, that is we will be traversing through the array and displaying elements one by one. This is your driver function. This is your driver function, wherein you are just declaring and initializing your arrays. This is your 1 array, this is your 2 array, and then you're calling this merge function directly, because we are using here, we have this static function over here, so we don't need to create objects. So we are directly calling merge, and we are passing array and the length of these two arrays, and then finally we are displaying the answer array, which is there because we are returning something from this function and we are storing in this array, and then finally we are printing out all the elements that are sorted in our answer array. So this is your driver function. Now let's try to implement it. So now you have your class over here, that is merge, and in this you have your static function, that is merge, and in this you have these 4 arguments, array 1, array 2, and the sizes. So you initialized your answer array, you declared and initialized your pointers. This is a while loop that will take care of comparison, and once one of these arrays is exhausted, then these while loops, this while loop and this while loop, take care of the rest of the elements, and then you return the answer array. You have this static function over here, that is display function. Another, you have your driver method over here, in which you are just initializing and declaring 2 arrays and calling the merge function and calling the display function. Now let's save this file and let's name this file as, just a minute. So the name, let's save this file and let's save it on the desktop and name this file as merge.java, right? And now let's open up our command prompt, and in this command prompt, let's type in javac merge.java to compile our program, and then write java merge to run our program. So you see, we have our sorted array, that is 1, 4, 5, 6, 8, 9, 10, 15, 20, 40, 55, and 92. And all the elements are sorted. So we have used a smaller implementation of merge function, which was there in merge sort, and we have solved this question. So there can be many questions based on merge sort. You need to check out and solve them with the help of this merge sort algorithm. So this is how you implement your merge function. Let's try to understand what is backtracking. So basically, a backtracking algorithm is one in which you explore all the different paths that are there. So let's suppose you have let's take an example wherein you're trying to find the sum of the you have these nodes. Let me just clear it out and let me just write it in this way. Okay, so you have a tree and it's a binary tree, not a BST. Okay, so we can have anything, right? So you have 3, then you have 2 over here, then you have 4 over here, then you have 30 over here, then you have 40 here. So now how backtracking works, it is a programming paradigm which checks all the possible paths. If you have seen my lecture that was earlier there, that is of greedy. So in that we will make a choice. Should I go for this or should I go for this? Since we are looking for maximum, we made a choice and we went for this. Now what happens in this? Okay, in backtracking, it will either go on this way or it will go on this way. Anyways, he's going to check all the different possible paths. So what he did, he first went on to this path and he calculated the sum. So he find out, okay, the sum of this is what, 70. Now he went again and went for this path. So okay, he find out, okay, now the sum is what, 90. Okay, done. So now he backtracks again. Now he checks. Okay, 538, that is 38. Okay, done. So 538, 48. So in order now, what he is doing, he's working in such a fashion that uh, if we obviously now we will this was our first step, right? And then we backtrack. This was our second step. Then we backtrack. This was third. This was fourth. Now once we don't have any steps, or we are stuck, right? In this case, we are stuck over here. We don't have anywhere to go. So we backtrack. We went over here and calculated the distance. Now once we are stuck over here, we backtrack. We went to here and now calculate from here. So in this way, we are backtracking. We are going back to the point where we were stuck, and we were going back to the point where we find those alternate paths, right? You see, once we were here, we had two choices. One was here, one was here. Now we went for this and we calculated the sum. Now we are stuck. We traversed back to this point, right? And we went to this point. So this is how backtracking works. And non-recursive approach is not that much intuitive. And if you talk about recursive approaches are much more intuitive. So now let's try to understand, what do you mean by recursion and how does it work? You might be thinking, okay, sir, there is a similarity between a recursion and a backtracking. Yes, absolutely. The way you backtrack is there also. So now in recursion, what happens? It's a function that calls itself, right? So if you talk about a function and you are doing some stuff over here, and then this function is calling itself again. Now, obviously, there are three major parts in this, right? In recursion, what are those? So first is let's skip for now. Let's not talk about technical terms. First, let's try to cover these things. Okay, so recursion is nothing but a function calling itself. So there's a function. Inside that function, it's a function that's calling the same function again. So this is your recursion. Now it comes intuitively when a function is breakable into sub problems. Now when your problem is divided into sub problems, right? So let's suppose you are saying that okay recursion, calculate the sum of this. Let's suppose this tree was there, right? So now what recursion did, he said, okay recursion, calculate, I don't know, my sum is 5, calculate, add this 8 and then calculated sum. Okay, what recursion did, he added this with this and then he stopped. Okay, he said, okay recursion, the total sum is 13, we are 13 at this point. Now you go ahead and calculate the sum from this position. So now recursion is throwing us to the new alternative path, and then we are trying to calculate. So our problem, whenever we are in this situation wherein we are trying to find the we are able to break our problem into sub problems. At that time, we can easily go for recursion. There are many data structures which are recursive in nature, like you have trees, you have graphs. So those are recursive in nature. And if you try to solve those problems without using recursion, it will be much more difficult. So in those algorithms, you might have seen in order traversals, right? In order, post order, and pre-order, right? So in that, if you don't use recursion, then you have to write a lot of code. If you're writing only in order function, you just have to write 3 lines of code. That's it. All of them are recursively calling the in order function again and again. 3 lines, done. You are able to traverse through the whole tree, right? It same goes for post order, same goes for pre-order. So these are recursive in nature, and if you try to solve these problems based on this using recursion, it's much more easy. Okay, so now this is what a recursion is. Now talking about 3 parts, right? So now you have a function, and in this you have a function again, and it's calling itself again. So the first thing that comes up in your mind is that if this function is calling itself again and again and again, so will there be a stack overflow? Yes, there will be a stack overflow. Why? Because you don't have any base condition saying that okay, stop when you are executing 5 times or 10 times. Okay, so that base condition should be there. Okay, that is a base condition which tells that you should stop. Then you have the logic, whatever you want to do. Okay, let's suppose you are trying to print on I write SOP, right? That means system.out.println or printf in C. Okay, so I'm writing printf hi. So now basically I'm trying to print this again and again and again. Okay, done. And then you have your recursive call, which is function which is calling itself again and again. Okay, so now let's try to see 2 things. What is an activation record? And how does this backtracking, how is that thing happening in this recursion? Okay, so now let's suppose you have a function and it takes in an argument as n. Okay, so now our n is currently what? Let's suppose our n is 0, and we want to print the numbers from 1 to 5. So this was also asked in one of the interview questions, that you need to print numbers from 1 to 5 without using any for loop. Okay, so at that time you can easily go for recursion. Now how you can go for recursion? You write the function. Obviously it's not returning anything. Now you have void. Now the base condition, if n is equal to 5, or if n is equal to 5, that means you're trying to print the numbers from 1 to, if you're going from 0 to 5 or including 5, so you write it 6 over here. If you're going for 5 only, then you write if you're going less than 5, that means 0 to 4, all these numbers should be printed, so you go for 0 to depending upon whatever the requirement is. That's it. It is obviously independent of whatever you write. So it's not that it is always this what you have to write. So it is independent. It depends upon your problem. Okay, so now let's suppose I wrote 6. That means I am printing 0 to 5. That means 6 elements. Okay, so now if that is the case, when we are here, we return. Okay, else what we do, we SOP, that means we are printing n. Okay, and then what we are calling recursive function again, but this time with updated arguments. That means we are incrementing our n, because earlier it was 0. So earlier we had 0. So now how this thing is happening? Now you might be thinking, okay sir, this is okay, that you're teaching this thing, this is okay. Now how is this backtracking happening here? Here you won't see that much backtracking. Why? Because after the function call there are no statements to be executed. So now let's try to first understand the activation record, that means the stack that is created in the recursion, how the calling happens. Okay, so now this is your first activation record. This will execute at n is equal to 0. Let's name this as first step, let's name this as second, and let's name this as third step. Okay, so now what happens, you're trying to calculate what you're trying to execute the first statement. So you check n is equal to 6. No, it was not equal to 6. So this step is done. Then you print. So SOP, you are printing. So this step is also done. Your output will start executing. Your output will be 0 first. Then the function is calling itself. Now this third execution, this third step will be executed. Now function will be called. Okay, so it will be called at n equal to 1. So same thing happens. 1, 2, and 3 will be executed. It will be called for n equal to 3, and so on. So 1, 2, 3, all these statements will be executed. But once you are at n equal to 6, at that time it will return, and it will go back to n equal to 5. Then n equal to 4, then equal to 3, then n equal to 1, and then finally n equal to 0, and then to the main function who called this function. Now you might be thinking, okay, sir, backtracking is happening, but that is happening at the end. Okay, so now this is the recursion, that the backtracking is happening at the end. Now even if you are using the non-tail recursion, wherein that is something that will fall under the recursion. If you are using a non-tail recursion, or if you are using a tail recursion, that means your recursive call is at the end, so there will be no extra space that you will be using, because you don't have any statements to be executed at the end. So this is a non-tail, this is a tail recursion. That means your recursive call is at the end, so this space will not be over here. Okay, so now if I just change this statement from SOP this position to this position, okay, now let's see what happens. Okay, I'm printing this end statement, and now this is not a tail recursion. Okay, you don't have you have statements after the function, after the recursive call. So let me just quickly clear out this, and let me just write it again. So you have function and it's expecting as int equal to n. So now what you are doing, you have this recursive call. You are saying that, okay, from n equal to, let's put less values. So n equal to 3. So 0 to 2, that means 3 value you are returning. Okay. So now after that, your function calling itself, you're calling the function itself, and you're doing n plus 1, and then you're doing SOP n. Okay, that's it. Okay. So now how activation record will be there, how it will be there. So first activation record, it will be for n equal to 0. You check, is n equal to 3? No, it is not. So this statement is done. So let's name these statements 1, 2, and 3. Okay. So now you check for fun equal to n plus 1. So now at this position, the function will be called, and this statement is left behind. Okay. So now it will be called for n equal to 1. Again, it will be checked. No, it is not equal to 3. And then again, this function will call at n equal to 2. So this statement is left. So again, 1, 2, and 3 will be calling at n equal to 3. So this function will be called. So now you see, we didn't print any statements, right? So now what happens, what we do, now we do this thing. So now what, at this position, n is equal to 3. So now we return. So now we are backtracking. Okay. So that is why I said that recursion is much more intuitive. Okay. So it is much more intuitive. So now we backtrack. Now this three statement, that third statement was left for execution, and we are printing the value of n. So here we are just printing the value of n, and at this position n is equal to 2, so 2 will be printed. Now at this point we explicitly made him return, or it was that we were saying that return. Here this is an implicit return, so since there are no statements to be executed, it will return to the caller, that means who called it. So it was n equal to 1. So here again you will see, okay, this statement is left to be executed, so you will print 1. So again it was implicit recursion, implicit backtracking. So again you will backtrack to this position and you will print n equal to 0. So in this way, just by changing a single statement, you were able to reverse the order. Okay, so earlier what we had 0, 1, 2, and this time just by changing this simple SOP statement, we had 2, 1, 0. Okay, you are able to understand this base condition that is there. This is your base condition, right? This is your logic, that whatever you are doing, or not logic is over here. Obviously this is a simple example, so logic is over here, so that you are printing out statements, and then you have your recursive call, which is this rat in a maze. So basically you have a maze, and now let's consider this maze as a 2D array, that is 3 cross 3 array, and you have to reach from this source to this destination. Okay, now you have to reach from this to this, and plus there are some ways. Obviously now this is a rat, and that rat is in a maze. Now what is there? So basically whenever you have a 0, that means you can go ahead, so you can move the rat. Obviously this is a rat, and if there's a 0, so if there's a 0, right, and that means we have another 0 over here, that means rat can move in this direction. If there's a 1, that means rat cannot move. So 0 represents you can move, 1 represents you cannot move. Similarly, now this rat can move in 4 directions, that is up, right, left, and down. Okay, so now if there is 1, you cannot move. Now if there is, again, if there's a 0, you can move. If there is 0, you can move. Okay, so now you see over here what happens. Here at this position you have two choices, because here you cannot move, but here once going here, obviously you cannot move in this direction, because that is not, you cannot move. That will happen when you're dealing with n queen problem. That is also a one more example wherein you can move in this direction, in diagonal directions, right? We are not covering that thing in over here. We are just focusing on these simple direction, that is up, left, right, and down. Okay, so now obviously you cannot move in this direction. Let me just erase this thing again. Yeah, so now what happens? Okay, so now what is happening? It moved to this direction. Now here it had choice, so it can either go in this direction or it can either go in this direction. So let's suppose if it goes in this direction, and here I wrote 1, so that means here it had 3 choices. He cannot go here, he cannot go here, he cannot go here. So now he said that, okay, the choice that earlier, whatever the choice I made earlier was wrong, so now I need to backtrack. So what you did, you backtrack to this position. Now here is the choice. Obviously you need to keep track of that. You don't fall into a loop that you're just moving from 0 to 0, 0 to 0, then again from 0 to 0, like you're not moving from here, then here, then here, then here. So you need to keep track of that thing, which we'll see in the algorithm, how to keep track of that thing. But now once we are backtracking, now we see, okay, this path is there and it has not been iterated, or we haven't traversed through this path, so let's go through this path, because this path was nothing and we were not able to reach the destination. So we backtrack and we went over here. So now let's suppose we have 0, 1 over here, and we add 0 over here. So now we checked, okay, here we cannot go on this side, we cannot go on this side we have already executed, and now we cannot go on this side. Obviously diagonals are not possible, so we went on to this side, and finally we went on to this side. So we need to just write, if there is a path, we write yes, or if we want to calculate the number of possible paths, that means how many other paths are there. So let's suppose this would have been not 0, if it would have been 1. So at that time, what we can do, we can obviously traverse from this side and we reach this. We can also traverse from this side and reach this. We can also traverse from this side and reach this. So we had total of 3 paths. If our output will change, if our this maze will change. Okay, so this is the problem, that you need to calculate all the possible paths from reaching to source to destination. That means rat is there and it will have to reach to the end of the maze. That means this is the problem. Okay, this is your problem statement. Now let's move ahead and let's check this problem over here. So now the main method, you see, I have kept a static one. You can obviously use a dynamic as well, dynamic array. Okay, So now you have this maze. This is your main method, right, guys? So I'm using Java. You can use any programming language. Okay, so now what is this? This is a 2D array, that is our maze, and we have 0 0 0, and then we have 0 0 0 0, and then we have 1 0 0 0. Okay, so this is our maze. Okay, and now what we are doing, we will call this solve method. Now let's try to let's try to dry run and see how many numbers, how many ways are there. Okay, so now let's try to dry run this example. 1 second. So let's see how many outputs should we get. So here you cannot go, here you can go. Okay, and after that you can go here, you can go here, and you can go here, here. Okay, so this is your one path. Then obviously you have a choice. You can go either from this side and go here and go here. So you have two. So then obviously now these two paths are done. Obviously now we can go over here and then go up and then go here, and then go here. So you have three paths. Now from this position, you can either go from this and then go this. Okay, so total number of outputs for this array should be 4. Okay, so now this is your array, or this is your maze, and now let's try to see what is there. So now what is in your solve method? So in our solve method, we have a Boolean array, okay, of same size. That is of in here, what was the size? So we have 3 rows and 4 columns. So same Boolean array will also be here. The size will be same as what? 4 cross 3. Now it is a Boolean array. Now why we need this Boolean array? Just to keep track of that thing which wherein I said that we don't want to now moving from 0 to 0 and then going back to 0 and 0 again. We don't want to fall in that loop wherein where whatever we path earlier traversed, we don't want to go to that same path. So we need to keep track of that thing. So we use a Boolean array of same size, right? So this is how we declare it, and then we call this rate that maze function over here, wherein we are passing the arguments as our array, the length of that array, which is the original array, and plus this new array that we created, the Boolean array, and the starting points, that is from 0 to 0. So this index 0 0. Okay, so these are the elements. This is our solve method. Okay, now this was our main method, that is our driver function. This is our maze method, and now we are finally at the last method, that is our maze method. Now what are the things that you should be able to traverse? What are the things that you should know, you should need? Okay, so now what we have in this maze method, we are checking for the is valid function. That means if we can move from this point to this point, that means what are the criteria? What are the criteria for that? First, let's check is valid function. So is valid function is that function which takes an argument. Let's try to understand the is valid function. So obviously it should be greater than or equal to 0, right? It should not be something that we are looking for this position, which is outside the array, right? So for I as well as for j, okay? So you can easily change it, okay? This is something that is not dependence. These will remain same for every programming language. Obviously the syntax will change, but the algorithm will remain the same. So now obviously you don't want to go from this position to this on the left hand side or from the above. So you need to keep track of this thing, that this j is greater than or equal to 0, okay? Not something that is negative. Okay, now obviously now you don't want it to be negative. Obviously you don't want it to be something that is greater than the size, that is on this side or on this side. Okay, so these are the 4 conditions that you need to check first. And also that a of ij, that means this index should not be 1, because 1 represents that we cannot move. So once these conditions are satisfied, and plus that it should not be traversed, that Boolean array that we use, that for identifying that if this particular position has been traversed or not. So we check, okay, this should be false. If this is false, that means we are traversing for the first time, so we can traverse. So if that is the case, that means this position, obviously this should be 0. Now if this is the case, that means we can traverse from, obviously this is the starting index, and that means we can traverse from this position to this position. Okay, done. So these are the all conditions that we check for is valid. That is this path possible or not? Can we move from this position to this position? Done. If that is the case, we return true, else we return false. Okay, this is your is valid function. Now let's go back to the maze function. Now obviously once we are at the end of this position, that means this is our here we have rat and here is our destination, or you can say that this is the source and this is the destination. This is at the end. That means this here what should be the value of I? It should be n minus 1. That means if this is a 4 cross 3 matrix, that it means that the that row should be second and the column should be 3. So if we have reached at this position, that means we have a possible path. So we have this variable wherein we check for the number of possible paths. So we increment it. Okay, we just write C++, that means this is our one path, and then we return. Okay, now this is the Boolean array, and we checked. Okay, now if this is not the case, if this criteria is not met, that means we are not at the end. What we will do, we'll check. Okay, now first what we do, we write this thing as true. That means we are traversing this particular path. So we are at the starting, and now what we are doing, we have traversed this path, so we write here true. Okay, done. And then what we are checking, is this path possible, the upwards. Okay, so that is why we have written I minus 1, that is 1 above. Okay, so if you talk about this indexing, that 0, 0, 0, 1, 0, 2. So if we move something that is upwards, okay, so now what should be the row number over here? So row should be minus 1, obviously, and this should be 0. So you see the decrement over here. So that is why we are doing a decrement here. Okay, so we are checking, is the above path, is there a path that is above this, right? Above this position, is there a path? We checked, is valid. So is valid returned false. So there is no path. So this will not be executed. So this will not be, then we check, is there a downwards path? So let's suppose there was a 1. So there is not also a path. Now, again, is there a rightwards? If can we move from this position to this position? Let's suppose this was a 0. So yes, we can. So that is why we have 0 and 0, and this is 0 and 1. Okay, no. So this is a plus I. So that means we are traversing, there should be a path downwards. Okay. So now if this is the path, that means this is a j plus 1. That means this is a 0, 1 path. So this was not. So for example, there is no path as this as well. So this is 1, and we cannot check this one. So not a possible path from this side, not a possible path from this side, not a possible path from this side. So this is 0, 0, and we can traverse from 0, 0 to 0, 1. So 0, 1 means that j is incrementing. So you see the j incrementing over here. So we can traverse. So now once this is done, once we have returned, okay, this is a true, this is a valid path, then what we did, we again called this maze, but this time we are at this position. Okay. Okay. So now once we have that exact, all the possible paths we have traversed, then after traversing back, and then we will just update this to false. So just that if we don't have any paths from this position, let's suppose we were here, and from this we don't have, we had this one over here, and we are now stuck, right? Now we are stuck. Since we have already calculated this as true, now we don't have any path from this side. What we did, we traversed back, okay? Because this statement is still to be executed, okay? So we traversed back, and now once we are at this position, we said, okay, now we don't have any path on this side. So please update this to false again, because we are not able to find anything, okay? So we had this false again, and now once we are done, now what we do, we just traverse now this time to downwards, okay? Then we update this position to true again. So try to dry run this, guys. So this is very intuitive, okay? Just try to dry run this example and you will understand what is happening exactly. So once we are done with this, we will be able to find all the possible paths, okay? So now this is your maze function and this is your valid function, and that's it. This is all that you need to do in a rat in a maze problem, okay? You see how recursion was there, how recursion is much more intuitive. In this example, we are recursively calling for all the possible paths and then we backtrack. That's it. Done.
Now let us quickly summarize the video. In today's video, we discussed what are algorithms and how does algorithmic analysis help find time and space complexity, greedy programming and its implementation using Fractional Knapsack and Prim's algorithm, dynamic programming concept, divide and conquer and its implementation using merge sort and quick sort. We also learned about backtracking and recursion with an implementation. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions and I will respond to your comments.